Aboard your spacecraft, you're drifting through deep space right now, far from Earth, surrounded by stars in every direction. And from here, you can see what they truly are, rather than just points of light in a dark sky. Some stars appear as tiny orange embers, barely brighter than the darkness around them, while others blaze so large they fill your entire field of view, farther than the distances at which planets orbit our sun. The variety is truly staggering. The range from smallest to largest is almost impossible to comprehend, spanning from objects smaller than Saturn to spheres wider than Jupiter's orbit around the Sun. Out here, among them, floating between these distant suns, the scale becomes real in a way no photograph or diagram can convey. The smallest stars drift nearby, red dwarfs that glow with a gentle orange light, their surfaces cool by stellar standards, their sizes surprisingly small considering they are fusion-powered suns. These tiny stars measure only about 10 to 20% of our sun's diameter, making them roughly the size of Jupiter, or slightly larger. And from this distance, you could almost mistake them for planets, except for the light they generate from their own cores. The minimum size for a star is determined by whether it can achieve fusion in its core. These tiny suns pack enough mass to ignite fusion in their cores, but only barely, their internal temperatures and pressures just crossing the threshold required to fuse hydrogen into helium. The smallest confirmed star discovered so far carries the catalogue name EBLM J055557AB, and this dim red object measures only 8% larger than Saturn, making it the smallest known star in the universe. You are listening to the Drowsy Astronaut, and tonight we explore 100 peaceful facts about stars, drifting through the cosmos to witness the lights that fill our galaxy and eventually helped create us. Beyond the windows of the spacecraft, countless stars drift silently past. Some are tiny and dim, others impossibly large. And tonight, we take our time getting to know them. Before we begin, feel free to share your corner of the world and what time it is for you right now in the comments below. It still amazes me to see so many of you listening from all over this tiny little planet we call home. So make yourself comfortable as we begin with the smallest stars in the galaxy and slowly make our way toward the largest known suns in the universe. Red dwarfs, like the tiny EBLM we talked about, glow with a dull orange or deep red light, and their surface temperatures measure only about 3,000 degrees Celsius compared to our sun's 5,500 degrees. The cooler temperature results directly from their small size and low mass, the weaker gravitational compression in their cores producing less intense fusion and therefore less heat and light. A red dwarf might contain only 8 to 50% of the sun's mass, and this limited fuel supply burns so slowly and efficiently that these stars will continue shining for trillions of years. The universe itself is only about 14 billion years old, meaning no red dwarf has ever died of old age, and none will for hundreds of times the current age of the cosmos. Proxima Centauri, the nearest star to our solar system, at just over 4 light-years away, glows as one of these red dwarfs, measuring about 1/7 the sun's diameter and shining with a dim reddish light invisible to the naked eye from Earth. If you approached Proxima Centauri in a spacecraft, the star would appear as a small orange sphere, perhaps the size of Jupiter, but slightly larger. Its surface mottled with darker and lighter regions where convection brings hotter material up and cooler material down. The light from this star provides only about 1/6000th the luminosity of our Sun, requiring planets to orbit extremely close to receive enough warmth for liquid water to exist. Proxima Centauri does host at least one planet, Proxima Centauri b, which orbits so close to its dim sun that 1 year there lasts only 11 Earth days. Brown dwarfs drift in the space nearby, even smaller than the tiniest red dwarfs, objects that tried to become stars but failed to reach the mass needed for sustained fusion. These failed stars are larger than planets, but smaller than true stars, typically measuring between the size of Jupiter and about 8% of the Sun's diameter, ranging from about 13 to 80 times Jupiter's mass. They glow faintly from leftover heat from their formation and from occasional deuterium fusion, but they never achieve the sustained hydrogen fusion that defines a real star. The boundary between the largest planet and the smallest brown dwarf remains somewhat unclear, and the boundary between the largest brown dwarf and the smallest star sits at about 8% of the Sun's mass, where fusion becomes sustainable. Brown dwarfs appear even dimmer and cooler than red dwarfs, with surface temperatures sometimes dropping below 1000 degrees Celsius. Cool enough that some have weather, including clouds made of iron droplets or silicate particles drifting through their atmospheres. The coolest brown dwarfs glow mostly in infrared wavelengths, their surfaces barely warmer than a hot oven on Earth. And they blend into the darkness of space, nearly invisible except to sensitive infrared telescopes. From a spacecraft nearby, a brown dwarf might look like a dark reddish sphere, faintly luminous, more like a very hot Jupiter than like any star you would recognize. These objects bridge the gap between planets and stars, reminding us that nature does not always create sharp boundaries between categories. Moving away from the smallest stars, you approach a yellow star that appears familiar, a sun very much like our own, and this represents the middle range of stellar sizes. Our sun measures about 1.4 million kilometers in diameter, which equals about 109 Earth's diameters, large enough to fit over 1 million Earths inside its volume. From the perspective of stellar sizes, however, the Sun sits comfortably in the middle of the range, far larger than red dwarfs and far smaller than the giants that dominate other regions of space. Our Sun contains about 73% hydrogen, 25% helium, and 2% heavier elements, and it fuses roughly 600 million tons of hydrogen into helium every single second in its core. The Sun has been burning steadily for about 4.6 billion years, and it will continue at roughly this same size and brightness for another 5 billion years before changes begin, making it a reliable and stable source of energy for Earth throughout the entire history of our planet. If you approach the Sun from space, it would appear as a brilliant yellow-white sphere, its surface showing granulation patterns where hot gas rises in the center of each cell and cooler gas sinks at the edges, creating a texture like enormous bubbles covering the entire star. prominences of hot plasma sometimes arch above the surface, following magnetic field lines. And darker sunspots mark regions where magnetic fields suppress convection and cool the surface slightly. The Sun is ordinary by cosmic standards, one of perhaps 200 billion stars in our galaxy, the reference against which we measure all others. Continuing outward, you encounter stars noticeably larger than the Sun, main sequence stars that burn hotter and brighter. Their increased mass, making them both larger in diameter and shorter-lived than smaller suns. Stars somewhat larger and hotter than the Sun appear white or blue-white, their higher surface temperatures shifting their color toward the blue end of the spectrum. Sirius, the brightest star in Earth's night sky, measures about 1.7 times the Sun's diameter and shines with about 25 times the Sun's luminosity. Vega, another prominent white star, measures about 2.4 times the Sun's diameter and radiates about 40 times as much energy. These stars burn hotter and faster than the Sun, their greater mass compressing their cores more strongly and driving fusion at higher rates, which makes them brighter, but also means they exhaust their fuel faster. Red giants appear ahead, enormous stars in the late stages of their lives, their outer layers expanded to tens or hundreds of times their original size. Arcturus glows orange-red in the distance, a star that was once similar to our Sun, but has now swollen to about 25 times the Sun's diameter. The star Aldebaran, the orange eye of Taurus the bull, measures about 44 times the Sun's diameter, large enough that if placed at the Sun's position, its surface would extend nearly halfway to Mercury's orbit. Red giants form when stars exhaust the hydrogen in their cores and begin burning hydrogen in a shell around the core, the outer layers expanding enormously while the surface cools and turns orange or red. If Arcturus replaced our Sun at the center of the solar system, its surface would extend roughly halfway to the orbit of Mercury, swallowing the inner solar system in its outer atmosphere. Beyond the red giants, you approach the realm of supergiants, stars so large that their scale defies easy comprehension, their diameters measured in hundreds of times the Sun's width. Betelgeuse dominates this region, the red supergiant that marks Orion's shoulder, a star that pulsates and varies in size, but averages somewhere between 700 and 900 times the Sun's diameter. If Betelgeuse replaced our Sun, its surface would extend past the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars completely within its outer layers. The star Antares, in Scorpius, measures roughly 850 times the Sun's diameter, another red supergiant nearing the end of its life, destined to explode as a supernova within the next million years or so. Betelgeuse appears distinctly reddish-orange to the naked eye from Earth, despite being about 540 light-years away. Its cool surface temperature of around 3,500 degrees Celsius, giving it that characteristic color. Rigel, another star in Orion, shines as a blue-white supergiant about 79 times the Sun's diameter. Smaller than Betelgeuse in size, but hotter and therefore more luminous, radiating about 120,000 times the Sun's energy into space. Blue supergiants burn incredibly hot, with surface temperatures reaching 10,000 to 30,000 degrees Celsius, and they live fast and die young, exhausting their nuclear fuel in just a few million years compared to the Sun's 10 billion-year lifespan. These massive stars form from clouds containing dozens or even hundreds of solar masses of material, and their intense gravity compresses their cores to such extreme temperatures and pressures that fusion proceeds at furious rates. The largest known stars exist at the far edge of this journey, hypergiants that push the limits of how large a star can physically become before instability tears it apart. Scuti, one of the largest stars known, measures approximately 1,700 times the Sun's diameter, according to current estimates, though the exact size remains uncertain due to measurement difficulties. Placing Scuti at the center of our solar system would result in a surface extending past the orbit of Jupiter, potentially reaching Saturn's orbit, depending on the star's current phase of expansion or contraction. The star appears unstable, pulsating and shedding mass through powerful stellar winds. And stars this large cannot maintain their size for long periods in cosmic terms. Stephenson 218, located in the constellation Scutum, potentially claims the title of largest known star, with an estimated diameter of about 2,150 times the Sun's diameter. Though again, uncertainty clouds the exact measurement. If this estimate proves correct, the star's surface would extend nearly to Uranus's orbit if placed at the center of our solar system, an almost incomprehensible size for a single object. These hypergiant stars are extremely rare. Only a handful exist in the observable galaxy, and they represent the final brief phase of very massive stars before they explode. These hypergiants exist at the absolute limit of what stellar physics allows, their immense size creating instability as the outer layers barely cling to the star. And when such a star finally exhausts its fuel, it explodes as one of the most powerful supernovae in the universe. The relationship between size and density creates an interesting pattern. The largest stars are actually the least dense. Their materials spread so thinly across such enormous volumes that they contain less density than Earth's atmosphere. A cubic meter of material from a red supergiant's outer layers would weigh less than the air you breathe. The gas, so diffuse, it would qualify as a vacuum by Earth standards. These enormous stars are held together only by gravity, the outer layers barely bound to the core, easily lost to stellar winds or pulsations. In contrast, the smallest stars pack their mass into tiny volumes, creating higher densities, though still nothing compared to the extreme densities of white dwarfs or neutron stars. Surface gravity varies dramatically with size. The largest stars have such low surface gravity that you could almost jump to escape velocity if you could somehow stand on their photospheres. The immense size means the surface sits very far from the star's center, where most of the mass concentrates, weakening the gravitational pull experienced at the surface. On Betelgeuse's surface, gravity would be only about 1/10,000th of Earth's surface gravity, nearly weightless by human standards. On a red dwarf, surface gravity would be much stronger, despite the star's small size, the compact nature, and proximity to the mass, creating a powerful pull. Most stars in the galaxy are actually small red dwarfs. The huge giants and supergiants you see here represent rare extremes, impressive to observe, but statistically uncommon. About 75% of all stars are red dwarfs, small, cool stars that will burn for trillions of years, far longer than the current age of the universe. Only about 1 star in 10 million grows large enough to become a hypergiant. These enormous stars require very high initial mass, and such massive stars are rare. The size distribution heavily favors the small end. Tiny stars dominate the galaxy, while giants remain spectacular outliers that draw attention through their brightness and scale. When you look at the night sky from Earth, however, you see mostly the larger and brighter stars, because the dim red dwarfs are simply too faint to be visible without telescopes, despite their overwhelming numbers. Viewing these stars from nearby, rather than from Earth's distant perspective, changes everything. The tiny red dwarf that appears invisible from Earth glows warmly here. A small, gentle sun, the enormous hypergiants that appear as bright stars from Earth, reveal themselves as incomprehensibly large structures, surfaces that extend across distances that would take light hours to cross. The scale becomes physical rather than abstract. Seeing a star that dwarfs our entire inner solar system makes the numbers real in a way that transcends description. You float among stars from the smallest to the largest, witnessing the full spectrum of size that fusion-powered suns can achieve. And the journey has only just begun. The stars surrounding your spacecraft display colors ranging across the entire spectrum, from deep blue through white and yellow to orange and red, each color revealing the star's surface temperature as reliably as a thermometer measures heat. Hot objects glow blue, cooler objects glow red, and this relationship holds true whether you are looking at a piece of heated metal, a flame, or a star millions of kilometers across and light years away. The hottest stars shine with an intense blue-white light, their surfaces reaching temperatures above 30,000 degrees Celsius, while the coolest stars glow dull orange or red at temperatures around 3,000 degrees Celsius, still hot enough to vaporize any known material, but cool by stellar standards. Looking at a star's color immediately tells you something fundamental about that star, and astronomers have organized this information into a classification system that groups stars by their spectral characteristics. The spectral classification system arranges stars into categories labeled O, B, A, F, G, K, and M, progressing from hottest to coolest, with each letter representing a range of temperatures and associated colors. O-type stars, the hottest, glow blue-white, with surface temperatures exceeding 30,000 degrees Celsius, while M-type stars, the coolest, shine with dull orange or red light at temperatures around 3,000 degrees Celsius, or even lower. Generations of astronomy students have memorized this sequence using the mnemonic, "Oh, be a fine guy, kiss me," or alternative versions using "girl" instead. The mnemonic serving as a simple way to remember the order, from hot to cool. Our Sun falls into the G category, technically classified as a G2V star, meaning it sits near the middle of the G-class temperature range and belongs to the main sequence, the V indicating this last detail in a system of Roman numeral classifications. Between the simple letter categories lie numerous subdivisions numbered 0 through 9, with G0 representing the hottest G-type stars and G9 representing the coolest. just before transitioning into K0, and this finer division allows astronomers to specify stellar temperatures with greater precision. The Sun at G2 has a surface temperature of about 5,500 degrees Celsius and appears yellow-white to our eyes, though from space without an atmosphere filtering the light. It looks more purely white, with just a hint of warmth. Stars slightly hotter than the Sun, such as F-type stars, appear more purely white, while stars slightly cooler, such as K-type stars, show a definite orange or peachy color. The difference may seem subtle when comparing similar stars, but place a hot blue O-type star next to a cool red M-type star, and the contrast becomes dramatic. One glowing electric blue, and the other burning dull crimson. The colors we see from stars result from a physical principle called blackbody radiation, which describes how hot objects emit electromagnetic radiation across a range of wavelengths, with the peak wavelength depending on the object's temperature. Hotter objects emit more energy at shorter wavelengths, which corresponds to blue light, while cooler objects emit more energy at longer wavelengths, which corresponds to red light. And this shift in the peak wavelength creates the color change we observe. A piece of iron heated in a forge demonstrates the same principle, glowing dull red when moderately hot, bright orange when hotter, yellow when very hot, and white or blue-white if you could heat it to extreme temperatures without melting it. Stars follow this same pattern on a grander scale, their colors revealing their surface temperatures through the unchanging physics of thermal radiation. Red dwarf stars glow with surface temperatures between 2,300 and 3,800 degrees Celsius, cool enough to appear distinctly reddish-orange. Barnard's star, one of the nearest stars to Earth, at just under 6 light-years away, exemplifies a red dwarf, too dim to see with the naked eye despite its proximity, shining with only about 0.04% the Sun's luminosity. Proxima Centauri, the very closest star at 4.24 light-years, also belongs to this category, a small, cool red star that would appear as a faint orange ember if viewed from nearby. These red dwarfs dominate the galaxy by numbers, but their dim light makes them invisible without telescopes from all but the closest distances. And only a handful of the nearest examples appear in catalogues of naked-eye visible stars. K-type stars, often called orange dwarfs when on the main sequence, or orange giants when evolved, shine with surface temperatures between 3,700 to 5,200 degrees Celsius, giving them a warm orange or peachy color. Arcturus, one of the brightest stars in Earth's sky, glows as an orange giant in the K class. Its cool surface temperature of about 4,300 degrees Celsius, creating its characteristic orange hue. Epsilon Eridani, a young K-type star about 10.5 light-years from Earth, represents an orange dwarf, similar to what our Sun might look like if it were cooler and slightly smaller. These K stars occupy a sweet spot in some astronomers' minds for potentially hosting habitable planets, because they live longer than Sun like G-type stars, providing more time for life to develop, while still offering more warmth and stability than the variable red dwarfs. G-type stars like our Sun appear yellow-white, with surface temperatures between 5,000 to 6,000 degrees Celsius. And this category includes many familiar stars visible from Earth. Alpha Centauri A, one component of the nearest star system, matches our Sun almost exactly in size, mass, and temperature. A G2 star just like the Sun, while Alpha Centauri B, its companion, belongs to the slightly cooler K1 category. Tau Ceti, another nearby Sun-like star at 11.9 light-years away, shines as a G8 star, slightly cooler and dimmer than our Sun, but similar enough to attract interest as a potential host for Earth-like planets. The Sun's yellow-white color appears slightly warmer than pure white, and this color derives from the peak wavelength of its black-body radiation curve, falling in the green part of the spectrum, though our eyes perceive the combined output across all visible wavelengths as yellowish white. F-type stars burn hotter than the Sun, with surface temperatures between 6,000 and 7,500 degrees Celsius, appearing white or slightly blue-white to our eyes. Procyon, the bright star in Canis Minor, shines as an F5 star, noticeably whiter than the Sun when viewed through a telescope, and it radiates about 7 times the Sun's luminosity from a surface area only slightly larger. Canopus, the second brightest star in Earth's night sky, after Sirius, glows as an F0 supergiant, enormously large and luminous despite its relatively modest surface temperature compared to truly hot blue stars. These F-type stars live shorter lives than G-type stars like the Sun, burning through their fuel faster due to their higher core temperatures and fusion rates. But they still enjoy lifespans measured in billions of years, rather than the mere millions that hotter stars experience. A-type stars appear brilliant white or blue-white, with surface temperatures between 7,500 and 10,000 degrees Celsius. And these stars include some of the most prominent objects in Earth's night sky. Sirius, the brightest star visible from Earth aside from the Sun, shines as an A1 star with a surface temperature around 9,900 degrees Celsius, blazing white, with about 25 times the Sun's luminosity. Vega, another famous A-type star, appears slightly cooler at A0 classification and serves as one of the standard reference stars for astronomical measurements, its pure white light defining the 0 point for several important stellar magnitude and color scales. Altair, the third star in the Summer Triangle, along with Vega and Deneb, also belongs to the A-class, completing a trio of prominent white stars easily visible from northern latitudes during summer months. B-type stars enter the realm of truly hot, massive stars, with surface temperatures between 10,000 and 30,000 degrees Celsius, and colors shifting from blue-white to deeper blue. Rigel, the bright blue supergiant in Orion, burns at about 12,000 degrees Celsius at its surface, appearing distinctly bluish to the eye and radiating about 120,000 times the Sun's luminosity into space. Spica, the brightest star in Virgo, shines as a B1 giant with a surface temperature around 22,000 degrees Celsius. Its blue color visible even to the naked eye under dark skies. These massive B-type stars live fast and furious, exhausting their core hydrogen in just 10 to 100 million years, depending on their exact mass. And they will end their lives as supernovae, rather than fading gently into white dwarfs like smaller stars. O-type stars represent the absolute extreme of hot, massive stars, with surface temperatures exceeding 30,000 degrees Celsius and sometimes reaching 50,000 degrees or higher, giving them an intense blue or blue-white color. Alnitak, one of the three belt stars in Orion, glows as an O9 star, while Theta 1 Orionis C, embedded in the Orion Nebula, burns even hotter as an O6 star with a surface temperature around 45,000 degrees Celsius. These stars are rare, making up less than 0.1% of all stars, but their enormous luminosity makes them visible across vast distances, and they play a crucial role in heating and ionizing the gas clouds around them. An O-type star might shine with the luminosity of 100,000 or even 1 million suns, flooding its surrounding region with intense ultraviolet radiation that strips electrons from hydrogen atoms and makes the gas glow in the characteristic red light of hydrogen alpha emission. The color of a star tells you not just its temperature, but also hints at its mass, its age, and its likely future, because these properties connect through the physics of stellar structure and evolution. Hot blue stars must be massive, because only massive stars generate enough gravitational pressure in their cores to sustain the high fusion rates needed to produce such intense heat and light. Cool red stars are generally less massive, their lower core pressures producing gentler fusion and dimmer, cooler surfaces. Though old, evolved stars can also appear red when they swell into giants, despite having started with more mass. A red star on the main sequence will live for trillions of years, while a blue star will live for only millions, the color serving as a clock, indicating how quickly the star burns through its fuel. The range of stellar colors creates a beautiful rainbow when you view a rich star field, each point of light contributing its own hue to the combined glow. Blue stars, scattered among white, yellow, orange, and red companions. The Pleiades star cluster showcases brilliant blue-white stars, born together only about 100 million years ago, their youth evident in their color and brightness. The Hyades cluster, older and closer, displays more yellow and orange stars, the hottest members having already died and left behind cooler, longer-lived companions. Globular clusters, ancient collections of hundreds of thousands of stars, glow with predominantly orange and red light, their blue stars long since dead, and only the cool, dim stars remaining from the original population, formed over 10 billion years ago. Understanding stellar colors transformed astronomy from a science that merely catalogued positions to one that could determine temperatures, masses, compositions, and evolutionary states of objects across the galaxy. The simple act of measuring a star's color through filters or a spectroscope reveals immediately whether that star burns hot or cool, young or old, massive or small. When you combine color information with brightness measurements, you can construct the Hertzsprung-Russell diagram, a plot that organizes stars by temperature and luminosity and reveals the main patterns of stellar evolution. Most stars fall along a diagonal band called the main sequence, running from hot, bright blue stars in the upper left to cool, dim red stars in the lower right, with giants and supergiants occupying a region above the main sequence and white dwarfs sitting below it, each region representing a different stage in stellar life. The spectrum of colors among stars exists because stars come in different masses, and mass determines temperature through the relationship between gravitational compression and fusion rate. A massive star compresses its core more strongly, heating it to higher temperatures, driving faster fusion, and producing more heat and light that makes the surface hotter and therefore bluer. A low-mass star compresses its core less, maintaining lower temperatures, fusing hydrogen more slowly, and producing less energy that results in a cooler, redder surface. The universe creates stars across a wide range of masses, from about 0.08 solar masses up to perhaps 200 solar masses or more. And this range of masses produces the range of colors we observe. The next time you look at stars in the night sky, try to notice their colors, the subtle differences that reveal so much about each distant sun. Betelgeuse glows noticeably reddish-orange, while Rigel shines blue-white, and comparing them shows the color contrast clearly even without a telescope. Sirius appears brilliant white, Arcturus warm orange, and our Sun, if you could safely view it against a black background, would show as yellow-white. Each color tells a story of temperature and mass, of youth or age, of furious burning or gentle simmering, and together they paint the cosmos in every hue from the hottest blues to the coolest reds. These colored lights emerged from clouds of gas and dust, places where gravity gathered material and compressed it until fusion began and stars were born. The space around your spacecraft grows hazy with dust and gas, not the empty vacuum of the regions between stars, but a cloud, a nebula, a place where stars are being born from the raw material of the galaxy. These giant, molecular clouds stretch across hundreds of light years. Enormous accumulations of hydrogen and helium, left over from the Big Bang, mixed with heavier elements scattered by earlier generations of stars that lived and died. The Orion Nebula spreads before you, the nearest major star-forming region, at about 1,344 light-years from Earth. A glowing cloud visible to the naked eye as a fuzzy patch below the three belt stars of Orion. Inside this beautiful chaos, gravity slowly gathers material into denser and denser clumps, each destined to become a star, or, for the smallest, perhaps a planet drifting alone through space. Star formation begins gently, not with sudden violence, but with the patient accumulation of mass as gravity pulls on the diffuse gas, filling the cloud. A region slightly denser than its surroundings will attract nearby material through gravitational pull, and as more mass gathers, the gravitational pull strengthens, drawing in more gas and dust in a gradual process that continues for hundreds of thousands of years. The cloud remains cold, typically only 10 to 20 degrees above absolute zero, and at these temperatures, the gas pressure provides minimal resistance to gravitational collapse. Slowly, over timescales longer than human civilization has existed, the gathering material forms a dense core, and this core continues contracting, growing smaller and denser and hotter as gravity converts potential energy into thermal energy through compression. The Eagle Nebula, home to the famous Pillars of Creation, demonstrates this process on a grand scale. Enormous columns of dust and gas, several light years tall, serving as incubators for new stars. The pillars consist of cooler, denser material that resists the eroding effects of ultraviolet radiation from nearby hot young stars. And embedded within these pillars, hidden from visible light but revealed by infrared observations, dozens of protostars are forming. The Carina Nebula, even larger and more active, contains thousands of stars in various stages of formation. From dense cores just beginning to collapse, to newborn stars that have recently begun fusion and are blowing away the remnants of their birth cocoons. These stellar nurseries glow with the light of their newborn stars, the hot young stars ionizing the surrounding hydrogen and making it emit the characteristic reddish light of hydrogen alpha radiation. As a collapsing core grows denser, it begins to spin faster, much like a figure skater spins faster when pulling in their arms, a consequence of the conservation of angular momentum. The rotation flattens the infalling material into a disk around the forming star, and this accretion disk plays a crucial role in the birth process, channeling matter onto the growing protostar and potentially forming planets in its outer regions. Material spirals inward through the disk, gradually adding to the central mass, and friction within the disk generates heat, making the disk glow in infrared wavelengths, even though the central object has not yet ignited fusion. The protostar at the center grows hotter as it contracts, its core temperature rising steadily, but it has not yet reached the 10 million degrees Celsius required to fuse hydrogen into helium. The protostar phase can last from 100,000 years for massive stars to several million years for stars similar to or smaller than the Sun, a period where the object shines through gravitational energy release rather than fusion. During this time, the protostar may be completely hidden within its dusty cocoon, visible only in infrared and longer wavelengths that can penetrate the surrounding material. Observations by the James Webb Space Telescope have revealed protostars in exquisite detail, piercing through the dust to show the structures of forming stars that remained hidden from previous telescopes operating at visible wavelengths. Within the Carina Nebula, within the Orion Nebula, within thousands of other star-forming regions across the galaxy, protostars by the millions are progressing through this phase, gathering mass, heating up, approaching the threshold where fusion will begin. When the core temperature finally reaches about 10 million degrees Celsius and the density becomes high enough, protons begin to overcome their electrical repulsion and fuse together, initiating the nuclear reactions that will power the star for the rest of its life. The ignition of fusion does not happen instantly, as a single moment, but rather builds up gradually as the fusion rate increases. The energy output rises, and the pressure from this energy release finally halts the gravitational collapse. The star achieves hydrostatic equilibrium, a balance between gravity pulling inward and radiation pressure pushing outward, and it settles onto the main sequence, beginning the long, stable phase where it will spend most of its existence. For a star like the Sun, this moment arrived about 4.6 billion years ago. For massive O-type stars, it might happen in only a few 100,000 years after collapse begins. And for the smallest red dwarfs, the journey from cloud to fusion might take tens of millions of years. The newborn star produces a powerful stellar wind, a stream of charged particles flowing outward from its surface. And this wind helps clear away the remaining gas and dust from the surrounding region. Over time, perhaps 1 million years or more, the remnants of the birth cloud disperse, blown away by stellar wind and radiation pressure, and the young star becomes visible at optical wavelengths. If planets formed in the accretion disk, they too emerge from the dissipating dust, settling into stable orbits around their new sun. Our solar system formed this way 4.6 billion years ago. The Sun igniting fusion, while Earth and the other planets condensed from the remaining disk material, and all the star-forming regions we observe today are creating new solar systems through the same process. Stars are often born in groups, multiple protostars forming within the same molecular cloud and remaining loosely associated as an open cluster after the birth cloud disperses. The Pleiades cluster, easily visible to the naked eye as a small group of bright blue stars in Taurus, contains about 800 stars born together roughly 100 million years ago from a single large cloud. The Hyades, another cluster in Taurus, hosts several hundred stars born about 600 million years ago, now slowly dispersing as their mutual gravity weakens and individual members drift away into the galaxy. These clusters provide astronomers with valuable laboratories for studying stellar evolution, because all the stars in a cluster formed at the same time from the same material, removing two major variables and allowing age-related differences to stand out clearly. The youngest stars display characteristics that distinguish them from older main sequence stars, including variability in brightness and the presence of strong stellar winds that create visible effects in their surroundings. T Tauri stars, named after the prototype T Tauri in the Taurus star-forming region, represent young sun-like stars that have not yet settled into stable main sequence burning, their luminosity fluctuating irregularly as they continue accreting material and adjusting their structure. Herbig Haro objects appear, where jets of material from young stars slam into surrounding gas, creating glowing shock fronts visible as small nebulous patches, often in pairs on opposite sides of the central star, where the bipolar jets emerge. The James Webb Space Telescope has imaged dozens of these objects in unprecedented detail, revealing the structures of the jets, the shocked gas, and the stars driving these outflows. Star formation continues throughout the galaxy, even today, billions of years after the Milky Way itself formed, because new clouds condense from recycled material, and old clouds that have not yet formed, stars continue their slow collapse. The rate at which stars form in our galaxy amounts to roughly 1 or 2 solar masses per year, meaning the galaxy creates the equivalent of one sun-sized star every year, or perhaps one massive star and several smaller ones adding up to the same total mass. Over the 10 billion year or so history of active star formation in the Milky Way, this steady production has created the 200 billion or more stars that populate the galaxy today. Some regions form stars more actively than others, with the spiral arms hosting most of the current activity, as density waves compress gas clouds and trigger collapse. The largest stars form from the most massive collapsing cores, regions that gather dozens or even hundreds of times the sun's mass before fusion begins. These massive protostars heat up quickly and begin fusion, while still accreting material, creating a complex situation where the star is actively pulling in mass while simultaneously blowing material away with its powerful stellar wind and radiation pressure. The formation of an O-type star, or a blue supergiant, represents an unstable race between accretion trying to add mass and radiation pressure trying to halt the infall. And the process can only succeed in particularly dense regions of nebulae, where the surrounding material provides enough momentum to force matter onto the growing star, despite the opposition. Once formed, these massive stars live brief, intense lives, burning through their fuel in just a few million years before exploding as supernovae. The smallest stars, the red dwarfs that dominate the galaxy by numbers, form from low-mass collapsing cores that take longer to heat up and require more time to gather sufficient mass for fusion to ignite. A collapsing cloud that will become a red dwarf might take several million years to reach the fusion threshold, much longer than the few 100,000 years a sun-like star requires. And during this extended protostar phase, the object remains dim and hidden. Once fusion begins, the red dwarf settles into a stable configuration that will persist essentially unchanged for trillions of years, far longer than the current age of the universe. The galaxy has never lost a red dwarf to old age, and every red dwarf ever formed still burns today and will continue burning for incomprehensibly long times into the future. Failed stars, the brown dwarfs, form through the same cloud collapse process, but simply do not gather enough mass to ignite hydrogen fusion. These objects might fuse deuterium, a heavier isotope of hydrogen, for a brief period. But this fuel runs out quickly, and the brown dwarf settles into a slow cooling phase, more like a giant planet than a star in its long-term behavior. The boundary between the smallest stars and the largest brown dwarfs sits at about 0.08 solar masses, or roughly 80 times Jupiter's mass, a threshold determined by the physics of hydrogen fusion and the gravitational pressure required to heat a core to 10 million degrees Celsius. Objects below this limit cool forever. Objects above it burn for eons, and the difference of just a few percent in mass determines which fate an object will follow. Current and future observations by the James Webb Space Telescope and other advanced instruments continue revealing new details about star formation, seeing deeper into the dusty clouds and imaging younger protostars than ever before possible. JWST's infrared vision cuts through the obscuring dust to show the hearts of stellar nurseries, revealing protostars still embedded in their cocoons, accretion disks around forming stars, and the structures of jets and outflows. Every observation refines our understanding of how stars form, how planets condense from disks, how binary and multiple star systems arise, and how the process varies depending on the mass of the collapsing core and the properties of the surrounding cloud. The same physics that created our Sun 4.6 billion years ago operates in these nebulae today, and we watch stars being born in real time, witnessing the process that gave rise to all the stars we see in the night sky. Returning your gaze to the visible stars scattered across space, you realize that every one of them emerged from a nebula like these. Every star condensed from a cloud. Every star passed through a protostar phase, and every star eventually ignited fusion and settled into its long, stable life. The smallest red dwarfs, the sun-like yellow stars, the blue giants, all began as collapsing cores in dark, cold clouds. All gathered mass from their surroundings, all heated up until fusion began. The process connects all stars to their nebula origins, and it continues throughout the galaxy, creating new stars that will shine long after the current generation has faded. These newborn lights will illuminate the galaxy of the far future, and some of them might host planets where life will develop, just as our sun's formation allowed Earth to exist and life to arise here. Looking out from your spacecraft, you allow your gaze to shift away from the distant nebulae and massive giants toward the familiar stars, the points of light that would be visible to someone standing on Earth tonight, looking up at a dark sky. These stars represent the ones that fill our night sky, the reference points by which humans have navigated and told stories for thousands of years. Each one a sun at a distance, each one contributing to the soft glow that lights the heavens when the moon has set. From a truly dark location, far from city lights, the human eye can see about 5,000 individual stars scattered across the entire celestial sphere, though from any one location at any one time. Only about half that number lies above the horizon. These visible stars represent just a tiny fraction of all stars in the galaxy, selected by proximity and brightness, rather than being a representative sample of stellar types. The brightest star in Earth's night sky goes by the name Sirius, located about 8.6 light-years away in the constellation Canis Major, the faithful dog following Orion the Hunter across the sky. Sirius shines with an apparent magnitude of -1.46, making it more than twice as bright as the next brightest star, Canopus. And its brilliance comes partly from being relatively nearby and partly from being intrinsically more luminous than the Sun. The light you see from Sirius tonight left that star 8.6 years ago, traveled through the empty space between there and here, and arrived at your eye having crossed about 81 trillion kilometers of distance. Sirius actually consists of two stars, Sirius A, the bright blue-white star we see easily, and Sirius B, a white dwarf companion visible only through telescopes and orbiting Sirius A once every 50 years. Canopus, the second brightest star, shines from much farther away at about 310 light-years, meaning its light has been traveling since the early 1700s, before arriving at Earth tonight. This F-type supergiant radiates about 15,000 times the Sun's luminosity, and its enormous energy output, combined with relatively reasonable distance, makes it appear very bright, despite being far more distant than Sirius. Alpha Centauri, the third brightest star to the naked eye, holds the distinction of being the nearest star system to Earth, at only 4.37 light-years away. A triple system consisting of Alpha Centauri A and B orbiting each other closely, plus Proxima Centauri, a red dwarf that orbits the pair at a much greater distance. Alpha Centauri A closely resembles our Sun in size, mass, and temperature. A G2 star, almost identical to the Sun, but viewed from the outside at a distance of 4.37 light-years. Arcturus glows as the fourth brightest star, an orange giant K-type star, about 37 light-years away, nearing the end of its life as it swells to about 25 times the Sun's diameter. When you look at Arcturus, you see what our Sun might look like billions of years in the future, when it exhausts its core hydrogen and begins its expansion into a red giant. Vega, the fifth brightest, shines blue-white, about 25 light-years away, a young A-type star that serves as a standard reference for astronomical magnitude scales. Capella, appearing sixth brightest, actually consists of 4 stars, 2 pairs of binary systems orbiting each other, the brighter pair being 2 yellow giants, somewhat more evolved than the Sun. These bright stars dominate the night sky from Earth, but they represent a biased sample, either nearby or intrinsically very luminous, or both, rather than typical stars. Polaris, the North Star, holds fame not for its brightness, but for its position in the sky, sitting almost directly above Earth's North Pole, and therefore appearing nearly stationary, while other stars wheel around it as the planet rotates. Polaris happens to lie very close to the point in the sky where Earth's rotation axis extends into space, making it useful for navigation in the northern hemisphere because it always indicates north and always stays at the same altitude above the horizon, equal to the observer's latitude. Polaris actually shines as the 48th brightest star, an F-type supergiant about 430 light-years away, intrinsically luminous, but appearing modest due to its distance. The position of Earth's rotation axis moves slowly through a cycle called precession, taking about 26,000 years to complete one circuit. And Polaris will not always be the North Star. In several thousand years, the axis will point toward different stars. Many stars visible to the naked eye turn out to be binary or multiple star systems rather than solitary suns, though usually only the brightest component can be seen without a telescope, while the companions remain hidden in the glare. Algol, the demon star in Perseus, consists of 3 stars, with the 2 closer components eclipsing each other every 2.87 days, causing the system's brightness to drop noticeably for several hours during each cycle. Mizar, the 2nd star in the Big Dipper's handle, appears as a close double in small telescopes, and spectroscopy reveals that each of these 2 stars is actually itself a binary, making Mizar a quadruple star system, while its naked eye companion Alcor may or may not be gravitationally bound to the group. Castor in Gemini appears as a single star to the naked eye, but consists of 6 stars in 3 binary pairs, all orbiting their common center of mass in a complex gravitational dance. The stars in constellations, those familiar patterns like Orion, Ursa Major, and Cassiopeia, appear to form groups in the sky, but actually lie at vastly different distances from Earth, their alignment being a matter of perspective rather than physical proximity. Orion's belt stars, Al-Nitak, Al-Nilam, and Mintaka, lie at distances of about 800, 1,340, and 900 light-years respectively, scattered across hundreds of light-years of depth, but appearing in a line because they all happen to fall in roughly the same direction as seen from Earth. The stars of the Big Dipper range from 80 light-years to 124 light-years away, again spanning a significant range of distances, despite appearing to form a pattern. These groupings are artifacts of human pattern recognition and historical tradition rather than reflecting actual structures in space. Some stars visible to the naked eye are remarkably luminous intrinsically, shining with the light of thousands or tens of thousands of suns, but appearing modest because of their great distances. Deneb, the bright star in Cygnus, radiates about 200,000 times the sun's luminosity from about 2,600 light-years away. A blue-white supergiant so intrinsically bright that it appears as one of the brightest stars in the sky, despite its enormous distance. Rigel in Orion shines with about 120,000 solar luminosities from about 860 light-years, another blue supergiant visible across vast distances. These extremely luminous stars are rare, but their brightness makes them visible across much of the galaxy, and they dominate the bright star population despite their rarity. Red stars visible to the naked eye include Betelgeuse and Antares, both red supergiants in late stages of evolution, approaching their eventual supernova deaths. Betelgeuse appears distinctly reddish-orange to the eye even in light-polluted skies. Its cool surface temperature of about 3,500 degrees Celsius, shifting its peak radiation into the red and infrared parts of the spectrum. Antares, whose name means rival of Mars because of its similar red color, glows in Scorpius as another red supergiant, cooler than the Sun at its surface, but enormously more luminous due to its vast size. Looking at these red stars, you see massive stars in their old age, having exhausted their core hydrogen and swollen to enormous dimensions as their internal structure evolves toward an inevitable explosive end. The stars twinkle when viewed from Earth's surface, a phenomenon caused by turbulence in Earth's atmosphere, refracting the starlight slightly differently from moment to moment, making the star's position and brightness appear to shimmer. From space, above the atmosphere, stars shine steadily, without twinkling, their light traveling through vacuum directly to your eye, without the distortions introduced by moving air masses. Planets visible from Earth typically do not twinkle as much as stars because their larger angular size averages out the atmospheric turbulence, the different parts of the planet's disk experiencing slightly different refractions that cancel each other, while a star's point-like appearance concentrates all the variation into a single shimmering point. Viewing stars from space eliminates this twinkling entirely, revealing the steady, constant light that has traveled years or centuries or millennia to reach this point in space. Most stars visible to the naked eye are more luminous than the Sun, a selection effect resulting from the fact that dim stars cannot be seen across large distances. The Sun, if placed at the distance of Sirius, would appear with a magnitude of about positive 1.4, fainter than Sirius itself, but still easily visible, while if placed at the distance of Arcturus, 37 light-years, it would shine at magnitude positive 2.7, comparable to Polaris. At the distance of Betelgeuse, about 540 light-years, the Sun would be invisible to the naked eye, requiring binoculars or a telescope to see. The vast majority of stars are actually less luminous than the Sun, red dwarfs and orange dwarfs that make up most of the stellar population. But these stars are too dim to see beyond a few dozen light-years, and none appear in the naked eye catalogue, despite being the most numerous type. Alpha Centauri stands as the closest star system visible from Earth, and its nearest component, Proxima Centauri, holds the title of closest individual star to the Sun at 4.24 light-years. Proxima Centauri is too dim to see without a telescope despite its proximity. A red dwarf shining with only about 0.17% the Sun's luminosity, and you would need to be within about 1 light-year of it to see it as bright as the Sun appears from Earth. The next nearest stars after the Alpha Centauri system include Barnard's star at 6 light-years, a red dwarf also invisible to the naked eye, and Wolf 359 at 7.8 light-years, another dim red dwarf. The nearest bright star visible without optical aid is Sirius at 8.6 light-years, and the general pattern holds that bright stars tend to be farther away, while nearby stars tend to be dim red dwarfs, invisible to the unaided eye. The light from distant stars has been traveling toward Earth for years, decades, centuries, or millennia, depending on the star's distance, carrying information about conditions in that star at the time the light began its journey. When you look at Sirius, you see it as it was 8.6 years ago, while Betelgeuse shows you its state from 540 years in the past, around the time of the late 1500s on Earth. The light from Deneb has been traveling for about 2,600 years, meaning it left that star around the time of ancient Greece and has been crossing space ever since. Every photon carries with it a record of the star's temperature, composition, and motion. Information astronomers extract through spectroscopy and careful measurements to build our understanding of stellar properties. Looking at these familiar stars from space removes the distortions introduced by Earth's atmosphere and allows their true colors and steadiness to show clearly. Each star a constant point of light rather than a twinkling shimmer. Sirius appears brilliant blue-white, Arcturus glows warm orange, Rigel shines pure blue, and Betelgeuse presents its reddish-orange hue. All the colors clear and saturated, without atmospheric scattering. The stars fill the sky in every direction, thousands visible to the dark-adapted eye, even from space, where no atmosphere limits the faintest detectable magnitude. These lights have guided travelers, inspired myths, marked the seasons, and measured the passage of years for all of human history. And each one represents a sun around which planets might orbit, and where, perhaps, life might exist wandering at their own night sky. The stars we see from Earth form the familiar reference frame for understanding the broader population of stars throughout the galaxy. And though they represent a biased sample favoring brightness over typicality, they provide the examples most people know, the names and patterns that connect human experience to the wider cosmos. Moving forward through the facts about stars, we shift from what we can see to understanding how these stars live, spending most of their existence in a stable phase where they burn hydrogen steadily for millions to trillions of years, a phase called the main sequence, where balance and consistency define stellar behavior for most of cosmic time. The stars around you burn with a stability that seems eternal, each one balancing the crushing weight of gravity against the outward pressure created by nuclear fusion in its core. This balance, called hydrostatic equilibrium, defines the main sequence phase of stellar evolution, the long Middle Age where stars spend about 90% of their total lifetimes converting hydrogen into helium through fusion reactions that release energy steadily and predictably. A star on the main sequence has reached a configuration where the inward pull of gravity exactly matches the outward push from radiation pressure and gas pressure generated by fusion. And as long as hydrogen remains available in the core, this balance persists with only minor variations. The main sequence is not a location in space, but rather a phase in a star's life cycle, a period of stability sandwiched between the chaotic formation phase and the dramatic changes that come with old age. At the heart of every main sequence star, deep within a core compressed to incredible densities and heated to millions of degrees, hydrogen nuclei slam together with enough energy to overcome their electrical repulsion and fuse into helium. The sun's core, for example, reaches temperatures of about 15 million degrees Celsius and densities about 150 times that of water, creating conditions where proton collisions occur frequently enough to sustain fusion at a rate that balances the star's energy output. Every second, the sun converts about 600 million tons of hydrogen into helium. And while this sounds like an enormous rate, the sun contains about 2 times 10 to the power of 27 tons of hydrogen, enough to continue this process for billions more years. The mass converted to energy follows Einstein's equation, relating mass and energy, with about 4 million tons of mass transforming into pure energy each second. And this energy slowly works its way outward through the star until it reaches the surface and radiates into space as light. The journey of energy from the sun's core to its surface takes an extraordinarily long time, about 100,000 years or more, because photons created by fusion reactions scatter countless times as they bounce through the dense plasma of the star's interior. A photon might travel only a tiny fraction of a millimeter before being absorbed and re-emitted by an atom. And this random walk process repeats billions upon billions of times as the energy gradually diffuses outward from core to surface. By the time a photon finally emerges from the sun's surface, it has forgotten any directionality it started with. And the light we see today was actually created in the core tens of thousands of years before humans existed as a species. Once the photon escapes the sun's surface, it travels freely through space, taking only 8.3 minutes to cross the 150 million kilometers to Earth. Stars on the main sequence come in a wide variety of masses, from about 0.08 solar masses for the smallest red dwarfs, up to perhaps 150 solar masses or more for the largest blue giants. And this range of masses creates a corresponding range of lifetimes. Massive stars compress their cores much more strongly due to their higher gravity, driving fusion at furious rates that produce enormous luminosity but exhaust the hydrogen fuel quickly, while low-mass stars compress their cores less, fuse hydrogen slowly, and eke out their fuel supplies over immense time spans. A star 10 times the sun's mass might live only 20 million years on the main sequence, burning bright and hot and dying young, while a star 1/10 the sun's mass will live for several trillion years, longer than the current age of the universe by a factor of hundreds. Our sun, at 1 solar mass almost by definition, since this is the reference, will spend a total of about 10 billion years on the main sequence, converting hydrogen to helium in its core at a rate that keeps it shining steadily at its current luminosity. The sun is currently about 4.6 billion years old, meaning it has already completed roughly half its main sequence lifetime, and will continue in this stable configuration for another 5 billion years or so, before core hydrogen depletion triggers the changes. That will transform it into a red giant. During these billions of years, the sun's luminosity has increased gradually by about 30% since formation, because the buildup of helium in the core increases the mean molecular weight and slightly alters the core's structure. But the changes have been slow enough that Earth's climate has managed to remain within habitable ranges throughout most of this period. The relationship between mass and main sequence lifetime follows approximately an inverse cube law, meaning that a star twice the sun's mass lives about 1/8 as long, while a star half the sun's mass lives about 8 times as long. This relationship arises because more massive stars must be more luminous to support themselves against their stronger gravity, and luminosity increases faster than mass increases, leading to shorter fuel lifetimes for heavier stars. A star 20 times the sun's mass might radiate 50,000 times the sun's luminosity and live for only about 8 million years, while a red dwarf, 1/10 the sun's mass, radiates only about 0.03% the sun's luminosity and will live for tens of trillions of years. The most massive stars known, approaching 150 solar masses, live for only a few million years, brief cosmic candles that burn out almost as soon as they ignite by astronomical standards. Red dwarfs, the smallest and most numerous stars, represent the ultimate in stellar longevity. Their low mass and slow fusion rates allowing them to burn through their hydrogen supplies over timescales that dwarf the current age of the universe. Proxima Centauri, the nearest star and a typical red dwarf, has an estimated main sequence lifetime of about 4 trillion years, roughly 300 times the current age of the universe of about 14 billion years. This means that every red dwarf ever formed still exists today, still burning hydrogen in its core, still sitting on the main sequence, and not a single red dwarf has yet reached the end of its fuel supply and begun to evolve off the main sequence. The galaxy will look very different in the distant future when red dwarfs finally start to die, a future so remote that trying to imagine it strains our capacity for comprehension. Main sequence stars arrange themselves along a diagonal line on the Hertzsprung-Russell diagram, a plot of stellar luminosity versus temperature or color, with hot, bright blue stars at the upper left, the Sun and similar yellow stars in the middle, and cool, dim red stars at the lower right. This main sequence band contains about 90% of all visible stars at any given time, the remaining 10% being giants, supergiants, or white dwarfs in various post-main sequence phases. The main sequence exists as a diagonal rather than a horizontal or vertical line because of the physical relationship between mass, temperature, and luminosity. More massive stars must be both hotter and more luminous to maintain equilibrium against their stronger gravity. A star cannot choose its position on the main sequence independently. Mass determines temperature and luminosity through stellar structure equations, and the result is the observed diagonal band. The stability of main sequence stars makes them potentially hospitable environments for planets and life. The steady energy output, allowing surface temperatures on orbiting worlds to remain within relatively narrow ranges for billions of years. Earth has existed for about 4.5 billion years in the Sun's habitable zone, the region where liquid water can exist on a planetary surface. And the Sun's slow brightening over this time has not exceeded the capacity of Earth's climate system to adapt through carbon cycle feedbacks and other mechanisms. If the Sun were a more massive star, burning brighter and faster, the habitable period would be much shorter, possibly too short for complex life to evolve. While if the Sun were a small red dwarf, the habitable zone would be much closer and potentially subject to tidal locking and stellar flare effects. The Sun's position as a G-type star provides a reasonably long stable period, matched well to the timescales required for biological evolution. Stars more massive than about 8 solar masses follow a somewhat different path through their main sequence lives, burning hydrogen in their cores, but also developing different internal structures than smaller stars. Very massive stars have convective cores and radiative outer layers, the opposite of the Sun's structure, which has a radiative core and convective outer layers. And this difference affects how thoroughly the stars can mix fresh hydrogen into their cores. Massive stars consume their core hydrogen first and cannot easily replenish it from the surrounding layers, leading to relatively short main sequence lifetimes, while intermediate mass stars achieve some mixing that extends their fuel supply slightly. The Sun's radiative core prevents mixing, so the Sun will exhaust its core hydrogen, while most of the star's total hydrogen remains unused in the outer layers. About 90% of stars currently observed in the galaxy are on the main sequence, burning hydrogen in their cores and shining with the steady output characteristic of this phase. The remaining 10% includes red giants, white dwarfs, and various other post-main sequence objects, stars that have exhausted their core hydrogen and moved on to later evolutionary stages. The dominance of main sequence stars in the visible population occurs because stars spend most of their lives in this phase. The stable hydrogen burning period lasts much longer than the brief formation phase or the shorter post-main sequence phases that follow. A Sun-like star spends perhaps 10 million years forming, 10 billion years on the main sequence, and only about 1 billion years in all subsequent phases combined, making main sequence stars by far the most common type, simply because that is where stars spend most of their time. The main sequence provides a cosmic clock in some ways, allowing astronomers to estimate the age of star clusters by examining which stars remain on the main sequence and which have evolved off. When a cluster forms, all its stars begin on the main sequence at the same time, but at different positions along the sequence depending on their masses. Over time, the most massive stars exhaust their core hydrogen first and leave the main sequence, becoming giants or exploding as supernovae, while less massive stars continue burning steadily. By identifying the most massive stars still on the main sequence in a cluster, astronomers can determine the cluster's age, since that turn-off mass corresponds to the lifetime of stars just now leaving the main sequence. Young clusters show massive blue stars still on the main sequence, while old globular clusters show only stars less massive than the Sun remaining, the more massive stars having long since evolved and died. The equation governing stellar structure, which relates mass, radius, temperature, and luminosity, determines where a star sits on the main sequence and how it will behave throughout its hydrogen-burning lifetime. These equations arise from fundamental physics, combining gravity, thermodynamics, and nuclear physics into a framework that predicts stellar properties with remarkable accuracy. Observations of stars generally match the theoretical predictions quite well, validating our understanding of how stars work and giving us confidence in models of stellar evolution that extend beyond the main sequence into phases we cannot observe as directly. The main sequence represents stellar physics at its most straightforward: fusion balancing gravity, pressure balancing weight, and the simple conversion of hydrogen to helium proceeding at rates determined by temperature and density. Looking at the main sequence stars surrounding your spacecraft, you realize that these points of light, burning steadily for millions to trillions of years, represent the default mode of stellar existence. Stars spend most of their lives here, in this balanced state, converting hydrogen to helium at the rate required to support themselves against gravity. The Sun is a main sequence star, Sirius is a main sequence star, Proxima Centauri is a main sequence star, and the vast majority of points in the night sky mark main sequence stars at various masses, shining with the stability that defines this phase. This stability will not last forever. Fuel supplies are finite, but while they last, main sequence stars provide the steady light that illuminates galaxies, warms planets, and potentially nurtures the development of life across the cosmos. Many main sequence stars do not burn alone, however, and the next aspect of stellar life to explore involves the companionship of stars. The fact that most stars exist in binary or multiple systems where two or more stars orbit each other, bound by gravity into long-term partnerships. These stellar families add complexity and beauty to the cosmos, creating orbital dances that last for billions of years and producing some of the most interesting objects and phenomena in the galaxy. From eclipsing binaries to novae to the eventual collision and merger of white dwarfs into Type Ia supernovae. The journey continues from solitary stars to stellar companions. The stars drifting past your spacecraft often come in pairs or groups, gravitationally bound companions that orbit their common center of mass, while both or all burn hydrogen in their cores. About 85% of stars exist in binary or multiple star systems, rather than shining alone like our Sun. And this high fraction reveals that star formation tends to produce multiple objects from the same collapsing cloud, siblings born together and remaining bound by gravity throughout their lives. Binary stars range from pairs separated by vast distances, measured in thousands of astronomical units, taking hundreds of thousands of years to complete one mutual orbit, to extremely close systems where the stars orbit each other in hours or days, with their surfaces nearly touching. Each configuration produces different observable effects and teaches astronomers about stellar masses, sizes, and evolution through the ways the stars interact. Alpha Centauri, the nearest star system to Earth, consists of 3 stars bound together through gravity, 2 sun-like stars orbiting each other closely, while a distant red dwarf companion circles the pair at a much greater distance. Alpha Centauri A, a G2 star almost identical to our Sun, and Alpha Centauri B, a slightly smaller K1 star, orbit their common center of mass once every 79.9 years, at an average separation of about 23 astronomical units, slightly more than the distance from the Sun to Uranus. Proxima Centauri, a small red dwarf, orbits the AB pair at a distance of about 13,000 astronomical units, taking perhaps 550,000 years to complete one orbit, so distant that some astronomers have questioned whether it is truly gravitationally bound, or might be a temporary association. From a hypothetical planet orbiting Alpha Centauri A, you would see Alpha Centauri B as a bright yellow-orange star, varying in apparent size as it moves through its elliptical orbit, sometimes appearing large and brilliant, at other times smaller and less dominant, but always far brighter than any star appears from Earth. Sirius, the brightest star in Earth's night sky, reveals itself as a binary system when observed through telescopes. The brilliant blue-white Sirius A, accompanied by a much fainter white dwarf companion called Sirius B. The 2 stars orbit their common center of mass once every 50 years, with the white dwarf swinging around the much brighter main sequence star in an elliptical path that brings it as close as 8 astronomical units and as far as 31 astronomical units from Sirius A. Sirius B, despite being only about the size of Earth, contains roughly the mass of the Sun, compressed into white dwarf densities where a teaspoon of material would weigh tons. This tiny, dense companion remained undiscovered until telescopes improved enough to see it through the glare of Sirius A. And even today, it requires good seeing conditions and adequate aperture to observe visually the faint white dwarf, easily lost in its brilliant companion's light. Binary stars that orbit close to each other can produce dramatic effects when one star passes in front of the other as seen from Earth. A configuration, called an eclipsing binary, where regular dips in brightness mark the orbital period. Algol, known as the demon star in the constellation Perseus, provides the most famous example, a system where a dimmer but larger star periodically eclipses the brighter, smaller star, causing the combined light to drop by about 1 magnitude for several hours every 2.87 days. Ancient observers noticed Algol's variability, the star's regular dimming and brightening unusual among the otherwise steady points of light filling the sky, and various cultures interpreted this behavior as ominous or demonic, hence the name meaning demon's head in Arabic. Modern observations reveal that Algol consists of at least 3 stars, with the eclipsing pair orbiting each other rapidly, while a third more distant star orbits the pair at a greater distance. The orbital mechanics of binary stars provide one of the most reliable methods for determining stellar masses, the only direct way to weigh stars without relying on theoretical models. By measuring the orbital period and the separation of the 2 stars in a binary system, astronomers can apply Kepler's third law, combined with Newton's law of gravity, to calculate the total mass of the system. And if the individual motions of both stars can be measured, the mass ratio, and then the individual masses can be determined. Visual binaries, where both stars can be resolved separately in a telescope, allow the most straightforward application of this technique, while spectroscopic binaries, where the stars appear as one point, but their spectra show periodic Doppler shifts, provide mass information through the velocities inferred from the spectral line movements. These measurements have confirmed theoretical models of stellar structure by showing that mass, radius, and luminosity follow the relationships predicted by physics. Some binary stars orbit so close that they almost touch, their surfaces separated by only a few times their own radii. And at these small separations, tidal forces become significant, and material can transfer from one star to the other. Each star generates a region of space called its Roche lobe, the 3-dimensional surface within which material is gravitationally bound to that star. And when a star expands to fill its Roche lobe, gas at the inner Lagrange point can flow to the companion star through a process called Roche lobe overflow. This mass transfer creates some of the most interesting objects in stellar astronomy, including novae, X-ray binaries, and Type Ia supernova progenitors, all arising from material flowing from one star onto another in close binary systems. The transferred material often forms an accretion disk around the receiving star, spiraling inward while heating through friction and emitting radiation at various wavelengths depending on the temperature reached. Cataclysmic variables represent a class of binary systems where a white dwarf accretes matter from a companion star. Typically, a red dwarf or other low-mass star that fills its Roche lobe and transfers material onto the white dwarf. As hydrogen-rich gas accumulates on the white dwarf's surface, it compresses and heats until conditions allow hydrogen fusion to ignite explosively in a thin shell, producing a nova. A sudden brightening where the star increases in luminosity by thousands or tens of thousands of times over days or weeks before fading back to its pre-nova state. Novae can recur when enough material accumulates again, and some systems produce novae repeatedly on timescales of decades or centuries, earning the designation recurrent novae. These explosions do not destroy the white dwarf, unlike supernovae, but instead blow off the accumulated surface material while leaving the underlying white dwarf intact to continue accreting and eventually produce another nova. Type Ea supernovae, among the most luminous explosions in the universe and crucial tools for measuring cosmic distances, arise from white dwarfs in binary systems that accrete enough mass to exceed the Chandrasekhar limit of about 1.4 solar masses. At this critical mass, electron degeneracy pressure can no longer support the white dwarf against gravity, and the star collapses rapidly, heating the interior until carbon fusion ignites explosively throughout the star in a runaway reaction that completely disrupts the white dwarf. The explosion produces an enormous amount of energy, briefly outshining the entire galaxy, and the characteristic light curve and spectrum of Type Ia supernova make them identifiable across billions of light years. Because all Type Ia supernovae involve white dwarfs near the same mass limit, they produce fairly standardized luminosities, allowing astronomers to use them as standard candles for measuring distances to remote galaxies and revealing the accelerating expansion of the universe. Contact binaries represent the extreme of close binary systems, pairs where the two stars actually touch and share a common outer envelope of material while maintaining separate cores. These systems typically consist of two low to intermediate mass stars that orbit each other in just hours, their surfaces distorted into egg shapes by mutual tidal forces and the rapid rotation. W Ursae Majoris stars exemplify contact binaries, showing continuous variability as the star's elongated shapes rotate into and out of view, and as each star periodically eclipses the other. The combined light output varies smoothly rather than showing the sharp dips characteristic of detached eclipsing binaries. The changing projected area producing a more sinusoidal light curve. Contact binaries likely formed from initially separated stars that evolved and expanded until they merged into the current configuration. And they represent a stage in binary evolution that may eventually lead to the complete merger of the two stars into a single rapidly rotating object. Multiple star systems extend beyond simple binaries to include 3, 4, or even more stars bound together through hierarchical arrangements, where pairs orbit each other, and these pairs in turn orbit at larger distances. Castor in Gemini consists of 6 stars arranged as 3 binary pairs, each pair orbiting its own center of mass, while the 3 pairs orbit their mutual center of mass at much larger scales. Mizar in the Big Dipper also contains 6 stars in a complex hierarchical system, and these configurations demonstrate that star formation can produce elaborate structures from single collapsing clouds. The orbits in multiple systems must follow certain stability criteria to avoid ejecting members through gravitational interactions, typically requiring that inner orbits be much smaller than outer orbits, so that the inner pair can be treated as a single object for purposes of the larger scale motions. Binary and multiple star systems provide natural laboratories for testing stellar evolution theories, particularly when both stars formed at the same time from the same material and differ only in mass. By comparing how stars of different masses but the same age and composition have evolved. Astronomers can isolate the effects of mass on stellar development and verify that theoretical models correctly predict the progression from main sequence to giant phases. Clusters serve a similar purpose on larger scales, but binaries offer the advantage of being common and individually observable in detail, while clusters require statistical analysis of many members to reveal evolutionary trends. The agreement between observed binary evolution and theoretical predictions strengthens confidence in our understanding of stellar physics. Planets can exist in binary star systems, orbiting either one of the two stars in what astronomers call an S-type orbit, or orbiting both stars at a greater distance in a P-type or circumbinary orbit. Tatooine in Star Wars famously featured a circumbinary planet with two suns in the sky, and real examples of such worlds have been discovered through Kepler spacecraft observations and other means, proving that planets can form and remain stable in binary systems, despite the complex gravitational environment. The habitable zone in binary systems depends on both stars' luminosities and the orbital configuration, creating more complicated conditions than in single-star systems, but not preventing habitability in principle. Close binaries might make planet formation difficult in certain regions, but wide binaries allow planets to orbit individual stars with minimal perturbation from the distant companion. The formation of binary stars likely occurs through several different mechanisms depending on the specific circumstances, including fragmentation of the original collapsing cloud into multiple cores that each form a star, capture of one star by another during the chaotic early phases in a cluster, and disk fragmentation where the rotating disk around a forming star breaks up into separate condensations. Wide binaries, with separations of thousands of astronomical units, probably formed through cloud fragmentation or capture, while close binaries likely formed from disk fragmentation or from wider binaries that lost angular momentum through various interactions and spiraled closer together. Some binary systems may have started as triples or higher multiples and ejected members through gravitational interactions, leaving behind the surviving binary pair. Looking at the stars around you, the realization settles that most of them have companions, partners in a long gravitational dance that will continue for billions of years as both stars burn through their fuel supplies. Some binaries will experience dramatic interactions when one star evolves first and transfers mass to its companion, creating novae, X-ray sources, or other exotic objects, while others will evolve more independently, both stars eventually becoming white dwarfs, or one ending as a neutron star or black hole, while the companion continues burning. The binary nature of stars adds richness to the cosmos, creating complexity beyond what single stars alone would produce. And these partnerships reveal themselves through careful observations of motions, eclipses, spectral shifts, and gravitational interactions that betray the presence of companions, even when the individual stars cannot be resolved separately. Many of these binary stars will age together and eventually reach the end of their hydrogen-burning phase. Time passes, billions of years of steady fusion, and eventually, even the most stable main sequence star begins to feel the effects of fuel depletion in its core. The hydrogen that once filled the star's center has been converted to helium, the fusion ash accumulating as an inert helium core that cannot yet fuse because the temperature remains too low for helium fusion to ignite. With no fusion occurring in the core anymore, the energy generation that once balanced gravity shifts to a thin shell surrounding the helium core, where hydrogen still remains and continues fusing into helium. This shell burning causes profound changes in the star's structure. The core contracts under its own weight, while the outer layers expand dramatically, and the star begins its transformation into a red giant, leaving behind the main sequence after spending 90% of its lifetime in that stable configuration. The changes happen gradually, over tens or hundreds of millions of years, slow by human standards, but rapid compared to the billions of years the star spent on the main sequence. Our Sun will undergo this transformation in about 5 billion years, its core hydrogen depleting after approximately 10 billion years, total of main sequence burning. And the changes will alter the Sun beyond recognition. The core will shrink to a fraction of its current size, becoming denser and hotter, even though no fusion occurs there, while the outer envelope will swell to perhaps 100 times the current diameter, engulfing Mercury and likely Venus, and possibly reaching Earth's orbit. The Sun's surface temperature will drop from its current 5,500 degrees Celsius to perhaps 3,500 degrees Celsius, shifting the Sun's color from yellow-white to orange-red as the peak wavelength of its radiation moves toward longer wavelengths. Despite the cooler surface, the Sun will become far more luminous than today, perhaps 1,000 to 2,000 times its current luminosity. The enormous increase in surface area more than compensating for the lower surface temperature. Arcturus demonstrates what a star like the Sun looks like after evolving into a red giant. This orange star, shining about 170 times more luminously than the Sun, from a diameter about 25 times larger. Arcturus sits about 37 light-years from Earth and appears as a bright orange point, easily visible to the naked eye, the fourth brightest star in the night sky. And looking at it provides a preview of the Sun's appearance billions of years hence. The star has exhausted the hydrogen in its core and now burns hydrogen in a shell, the helium core slowly growing as the shell converts more hydrogen to ash and adds it to the core's mass. Eventually, when the helium core reaches sufficient mass and temperature, helium fusion will ignite, converting helium to carbon and oxygen through the triple alpha process. But this occurs only after the red giant phase has progressed for some time. Aldebaran, the orange giant in Taurus, provides another example of a star in old age, measuring about 44 times the Sun's diameter and shining with about 400 times the Sun's luminosity, despite a surface temperature of only about 3,900 degrees Celsius. The cool surface temperature gives Aldebaran its characteristic orange color, and the star appears distinctly colored even to the naked eye from Earth, located about 65 light-years away. Stars like Aldebaran and Arcturus represent the future state of all Sun-like stars, the inevitable result of core hydrogen exhaustion and the beginning of the complex sequence of changes that will eventually lead to the shedding of the outer layers and the formation of a white dwarf. These red giants are not yet at the end of their evolution, but they have clearly left the main sequence behind and entered a phase of active structural change. The expansion of a star into a red giant occurs because the shell burning produces energy at a higher rate than the stable core burning of the main sequence phase. And this excess energy inflates the outer layers like a balloon, pushing them outward against gravity. The expanding envelope maintains a roughly constant total luminosity profile, while the radius increases enormously, requiring the surface temperature to drop to maintain the radiative equilibrium between energy generation in the interior and energy radiated from the surface. The physics of stellar structure dictates that these changes happen together, linked through the equations governing pressure, temperature, and energy transport, and the star naturally finds a new equilibrium configuration as a red giant with a huge extended envelope surrounding a contracted inert core. The transition from main sequence to red giant passes through an intermediate phase called the subgiant branch, where the star has left the main sequence but has not yet expanded to full red giant dimensions. During the subgiant phase, the star's luminosity increases somewhat, and the surface temperature drops slightly as the envelope begins its expansion, creating a star slightly larger and cooler than during the main sequence, but not yet showing the dramatic changes of the full red giant phase. This phase lasts for a relatively short time compared to the main sequence lifetime, perhaps 1 billion years for a sun-like star, before the continued growth of the helium core and the increasing shell burning rate drive the star toward the red giant configuration. Observers of star clusters can identify the subgiant branch as a group of stars positioned between the main sequence turn-off point and the red giant branch on the Hertzsprung-Russell diagram. Some red giants vary in brightness, pulsating gently as the outer layers expand and contract in response to instabilities in the energy transport through the envelope. Mira, a star in the constellation Cetus, exemplifies this type of variable star, changing from magnitude 2, easily visible to the naked eye, to magnitude 10, requiring a telescope to see. Over a period of about 332 days, Mira variables, named after this prototype, are red giants or supergiants that pulsate with periods ranging from about 80 days to over 1,000 days. Their brightness changes, reflecting the changing size and temperature as the stars swell and shrink. The pulsation occurs because the envelope of a red giant can become unstable to certain modes of oscillation, particularly when the star reaches the asymptotic giant branch phase, a later stage where shell burning becomes more vigorous and the star's structure more delicate. Cepheid variables represent another important class of pulsating stars, though Cepheids are typically more luminous than Mira variables and pulsate with different mechanisms and shorter periods. Classical Cepheids pulsate because their envelopes pass through a zone where helium is partially ionized, and the changing opacity as helium ionizes and recombines creates a valve mechanism that drives regular pulsations. The period of pulsation relates directly to the star's luminosity through the period-luminosity relationship, longer period Cepheids being more luminous than shorter period ones. And this relationship makes Cepheids invaluable as distance indicators, since measuring the period reveals the absolute luminosity, which can then be compared to the apparent brightness to calculate distance. Delta Cephei, the prototype star for this class, pulsates with a period of 5.37 days, varying from magnitude 3.5 to 4.4, as it swells and shrinks rhythmically. RR Lyrae variables constitute another class of pulsating stars, typically older and less massive than Cepheids, and these stars pulsate with periods less than 1 day, usually ranging from about 0.2 to 0.9 days. RR Lyrae stars populate globular clusters, ancient stellar systems, where the lowest mass stars, still on the main sequence, are turning off and beginning their evolution toward red giants. And the presence of RR Lyrae variables in a cluster indicates the cluster's age and metallicity. Like Cepheids, RR Lyrae stars serve as distance indicators because their absolute luminosities are fairly standardized. All RR Lyrae variables shining with roughly the same intrinsic brightness, regardless of their exact period. And this standardization allows astronomers to estimate distances to globular clusters and to map the structure of the Milky Way's halo. The mass loss from red giants contributes significantly to enriching the interstellar medium with heavier elements synthesized during the star's lifetime. The strong stellar winds that blow off the outer layers carrying carbon, nitrogen, oxygen, and other elements into space. A red giant might lose mass at a rate of 10 to the -7 solar masses per year or more, shedding material gradually over hundreds of thousands or millions of years and returning a significant fraction of the star's mass to the interstellar medium. This enriched material eventually mixes with the general population of gas and dust in the galaxy and gets incorporated into new generations of stars and planets, spreading the products of stellar nucleosynthesis throughout the galaxy over billions of years. The Sun itself formed from material enriched by earlier generations of stars, the presence of heavy elements in the Sun's composition revealing that previous stars lived, fused heavier elements, and died before the Sun formed 4.6 billion years ago. The duration of the red giant phase depends on the star's mass, more massive stars passing through this phase more quickly, while less massive stars take longer. But in all cases, the red giant phase lasts only a small fraction of the total main sequence lifetime. For a Sun-like star, the red giant branch phase might last about 1 billion years, comparable to the time since complex multicellular life appeared on Earth, while the main sequence lasted 10 billion years. The brevity of the giant phase relative to the main sequence explains why most stars observed at any given time are on the main sequence. They spend most of their lives there and only briefly pass through the giant phases before ending as white dwarfs or exploding as supernovae. Looking at a snapshot of the galaxy today reveals mostly main sequence stars, with a minority of giants and other evolved stars, the population statistics reflecting the time spent in each phase. Stars more massive than about 8 solar masses follow a somewhat different evolutionary path, becoming supergiants rather than ordinary red giants, and eventually reaching conditions where carbon, oxygen, and heavier elements confuse in their cores. These massive stars build up onion-like layered structures with different elements fusing in concentric shells, hydrogen in the outermost burning shell, helium deeper down, carbon and oxygen in still deeper shells, and eventually silicon fusing to iron in the very center. This complex structure develops over only a few million years in the most massive stars, the rapid evolution driven by the high core temperatures and pressures that allow fusion of increasingly heavy elements. When the iron core reaches the Chandrasekhar limit, fusion can no longer provide pressure support, and the star explodes as a core collapse supernova. But stars like the Sun never reach this fate, lacking sufficient mass to fuse carbon and oxygen. The aging of stars transforms the galaxy over time, the oldest stars having already evolved through their giant phases and become white dwarfs or neutron stars or black holes, while younger stars currently on the main sequence will age and evolve in the future. In globular clusters, the most ancient stellar systems in the Milky Way, with ages exceeding 10 billion years, all stars more massive than about 0.8 solar masses have already left the main sequence and either died or evolved to white dwarfs, leaving only the lowest mass stars still burning hydrogen in their cores. By contrast, young open clusters like the Pleiades show many massive blue stars still on the main sequence, these stars having formed only about 100 million years ago and not yet having exhausted their core hydrogen. The progression of stellar aging creates a temporal sequence visible across clusters of different ages, each cluster showing a different stage in the process of stars leaving the main sequence and transforming into giants. Looking at red giants from your spacecraft, you see stars in transition. Objects that once burned stably for billions of years now undergoing dramatic internal changes as fusion shifts from core to shell, and the structure responds by expanding and cooling. Some red giants pulsate, breathing in and out over months or years, while others shine more steadily, but all share the characteristic enormous size and cool surface temperature that defines this phase. These aging stars will not remain red giants forever. The next phase of evolution involves either the ignition of helium fusion in the core for stars massive enough to reach the required temperatures, or the gentle shedding of the outer envelope to reveal the inert core as a white dwarf for lower mass stars. The journey of stellar evolution continues from red giants toward the final states where active fusion ends and stars settle into their long twilight as slowly cooling remnants. The red giant sways and pulses gently, and over hundreds of thousands of years, its outer layers drift away into space. Not violently expelled in an explosion, but slowly released as the stellar wind grows stronger and the tenuous outer envelope barely clings to the star. The mass loss accelerates as the giant phase progresses, the star shedding material at increasing rates until eventually the entire envelope has dispersed, leaving behind only the hot, dense core that once generated energy through shell burning. This core, now exposed to space for the first time in billions of years, glows intensely with residual heat, its surface temperature reaching 100,000 degrees Celsius or more. And the ultraviolet radiation from this hot core illuminates the ejected envelope, making the gas glow in beautiful colors as atoms absorb the high-energy photons and re-emit them at visible wavelengths. The result is a planetary nebula, one of the most visually striking objects in astronomy, despite having nothing to do with planets. The name arising from early observers who thought these fuzzy patches resembled planets through their primitive telescopes. The Ring Nebula in the constellation Lyra provides one of the most famous examples of a planetary nebula, appearing as a glowing smoke ring when viewed through a telescope. The roughly circular shell of gas expanding outward from the central white dwarf at about 20 kilometers per second. The nebula spans about 1 light year in diameter now, having expanded from the central star over the approximately 8,000 years since the envelope was ejected. And it will continue expanding and fading for another 50,000 years or so before dissipating into the general interstellar medium. The Ring Nebula displays beautiful colors in photographs, oxygen emitting green light, hydrogen emitting red, and helium contributing blue. Each color arising from specific atomic transitions excited by the ultraviolet radiation from the central white dwarf. To the naked eye from Earth, the nebula appears as a faint grey smudge about 2,300 light-years away, but long-exposure photographs reveal the intricate structure and vivid colors. The Helix Nebula, the nearest planetary nebula to Earth at about 650 light-years away, appears significantly larger in the sky than the Ring Nebula because of its proximity, spanning an angular diameter of about 15 arc-minutes, roughly half the angular size of the full moon. Through telescopes, the helix shows a complex structure with filaments and knots of denser material embedded in the expanding shell. These features probably arising from instabilities and clumping in the ejected envelope. The central white dwarf appears as a faint blue point at the center, its high temperature making it blue-white in color despite its small size. And this hot star provides the ultraviolet radiation that keeps the nebula glowing. The helix will fade over tens of thousands of years as the gas disperses and the central star cools, eventually leaving just the white dwarf surrounded by dispersed material now mixed into the interstellar medium. Planetary nebulae come in various shapes, some nearly spherical, others bipolar, with two lobes extending in opposite directions, and still others showing more complex structures with multiple shells or jets. The Cat's Eye Nebula displays an intricate, multi-layered structure with concentric shells suggesting multiple episodes of mass loss, while the Butterfly Nebula shows dramatic bipolar lobes, probably shaped by the presence of a binary companion or by the star's rotation and magnetic field. The shaping mechanisms remain somewhat uncertain. Binary companions, stellar rotation, and magnetic fields, all potentially influencing how the ejected material flows outward, and different nebulae likely form through different combinations of these factors. The variety of shapes adds to the visual interest of planetary nebulae and provides clues about the processes operating during the final stages of stellar evolution for Sun-like stars. The duration of the planetary nebula phase is relatively brief, about 10,000 to 20,000 years typically, before the gas expands to low enough density that it ceases to glow brightly and merges with the interstellar medium. This represents only a tiny fraction of the star's total lifetime, a visible display marking the transition from red giant to white dwarf, a cosmic fireworks show celebrating the star's transformation into its final form. During this brief window, the nebula enriches the surrounding space with elements synthesized during the star's lifetime. Carbon and nitrogen and oxygen, created through fusion, now spreading outward to mix with the hydrogen and helium that dominate the interstellar medium. Future generations of stars will form from material that includes contributions from countless planetary nebulae, each previous star adding its nucleosynthesis products to the galactic chemical evolution. At the center of the planetary nebula sits the remnant core of the red giant, a white dwarf about the size of Earth, but containing about half the Sun's mass, incredibly dense and incredibly hot, glowing white from residual thermal energy. This white dwarf represents the final fate of stars like our Sun. All stars between about 0.5 and 8 solar masses, ending as white dwarfs after shedding their outer layers through planetary nebulae. The white dwarf contains no energy source. Fusion has ended permanently, and the star shines purely by slowly radiating away the heat left over from its former life. Supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same quantum state. The white dwarf maintains a stable size despite having no internal pressure from fusion or thermal effects. The electron degeneracy pressure, depending only on density and remaining constant as the star cools. Sirius B, the famous white dwarf companion to Sirius A, exemplifies the white dwarf state. A star about the size of Earth, containing roughly the Sun's mass and orbiting its bright main sequence companion once every 50 years. The density of Sirius B reaches about 1 million grams per cubic centimeter, meaning a sugar cube-sized piece of this material would weigh about 1,000 kilograms. And this density arises because the entire mass of a star has collapsed to a volume comparable to a planet. The surface gravity on a white dwarf is about 350,000 times Earth's surface gravity, so strong that light leaving the surface loses energy climbing out of the gravitational well, a measurable redshift caused by general relativity rather than motion. Sirius B shines with a surface temperature of about 25,000 degrees Celsius, hot enough to appear blue-white in color. But its small size makes it only about 1/400th as luminous as Sirius A, despite the higher surface temperature. The composition of a white dwarf depends on what elements fused in the star before it died. And for stars like the Sun, the white dwarf consists primarily of carbon and oxygen, the products of helium fusion in the star's late red giant phase. More massive stars that fused heavier elements before becoming white dwarfs might have white dwarfs made of oxygen, neon, and magnesium, while the least massive stars that barely ignite helium fusion might produce helium white dwarfs composed of helium rather than carbon and oxygen. The material in the white dwarf's interior crystallizes at lower temperatures, the carbon and oxygen atoms arranging into a lattice structure, much like a diamond. And the center of a cool white dwarf might literally be a giant, crystallized sphere of carbon, the ultimate fate of the carbon created by helium fusion in the star's core. White dwarfs cool slowly over billions of years, their surface temperatures dropping as thermal energy radiates into space with no mechanism to replenish it. A newly formed white dwarf might have a surface temperature exceeding 100,000 degrees Celsius. But after 10 billion years, it might cool to only 5,000 degrees. And after 100 billion years, it could cool below 1,000 degrees. The universe is currently only about 14 billion years old. So even the oldest white dwarfs in the galaxy have not had time to cool to the theoretical end state called a black dwarf. A white dwarf that has cooled to the temperature of the cosmic microwave background and emits no detectable light. Black dwarfs remain theoretical, objects that will exist in the far future when the universe is hundreds of billions or trillions of years old. Cold, crystallized spheres of carbon and oxygen drifting invisibly through space. About 97% of stars will end their lives as white dwarfs. All stars with masses between roughly half a solar mass and 8 solar masses, following this path after shedding their envelopes through planetary nebulae. This includes our Sun, destined to become a white dwarf in about 7 to 8 billion years, first swelling into a red giant, then ejecting its outer layers, then settling into a white dwarf state where it will cool for the rest of cosmic time. Stars less massive than about half a solar mass would also become white dwarfs, But none of these stars have had time to evolve off the main sequence yet, the universe being too young for a star that small to exhaust its hydrogen. Stars more massive than about 8 solar masses avoid the white dwarf fate entirely, ending instead in supernova explosions that leave behind neutron stars or black holes. White dwarfs in binary systems can accrete material from their companions if the orbit brings them close enough. Hydrogen pulled from the companion star's outer layers, falling onto the white dwarf and building up on its surface. This accreted hydrogen compresses and heats under the white dwarf's strong gravity, and when enough accumulates, it ignites in a runaway fusion reaction that detonates across the white dwarf's surface, creating what we observe as a nova. The nova explosion blows off the accreted material at thousands of kilometers per second, brightening the system dramatically for days or weeks before fading. And the process can repeat, some white dwarfs experiencing recurrent novae as they continue accreting and exploding material every few decades or centuries. The white dwarf survives the nova, the explosion occurring only in the accreted surface layer, rather than disrupting the star itself. If a white dwarf in a binary system accretes enough mass to reach a critical limit called the Chandrasekhar limit, about 1.4 solar masses, the electron degeneracy pressure can no longer support the star against gravity, and the white dwarf collapses. The collapse triggers runaway carbon fusion throughout the white dwarf, the entire star undergoing nuclear fusion simultaneously rather than just the surface layer. And the result is a Type Ia supernova, a thermonuclear explosion that completely destroys the white dwarf. Type Ia supernovae reach a remarkably consistent peak brightness because they all involve white dwarfs reaching the same mass limit, making them useful as standard candles for measuring cosmic distances. Astronomers using the known intrinsic brightness to calculate how far away the supernova occurred. The white dwarf's ultimate fate depends on its circumstances. Isolated white dwarfs cool peacefully forever, while those in close binaries might nova repeatedly or eventually explode as Type I supernova. The planetary nebula and white dwarf represent a peaceful ending for stars, material gently returned to space rather than violently expelled, the core settling into a stable configuration rather than collapsing into something more exotic. The process enriches the galaxy with carbon, nitrogen, and oxygen, elements essential for planets and life, scattered through the planetary nebula to mix with the interstellar medium. Stars forming from material that includes these enriched regions will have higher metallicity, more carbon and oxygen available to form planets, and complex chemistry, a gradual increase in heavy element abundance over galactic history. Our Sun formed from material enriched by previous generations of stars. The heavy elements in our bodies and our planet created in earlier stars that died and returned their nucleosynthesis products to space, connecting us directly to the cycle of stellar death and rebirth. Observing planetary nebulae and white dwarfs provides glimpses of the Sun's future. Seeing what our star will become helps us understand its full life story, from birth to ultimate fate. The Sun will swell into a red giant, shed its outer layers in a planetary nebula, perhaps similar to the helix or ring, and leave behind a white dwarf about half its current mass that will cool for trillions of years in the darkness of space. The planets will be affected, the inner ones possibly consumed, the outer ones surviving in altered orbits around a fading ember the solar system transformed but not destroyed. The peaceful nature of this ending feels appropriate somehow. Stars living for billions of years deserve a gentle conclusion rather than violent destruction, fading gradually into the cosmic background while contributing their accumulated elements to future generations of stars and planets, and possibly life. Some stars do not end peacefully, and you witness now one of the most dramatic events in the universe, as a massive star reaches the final moments of its existence and explodes in a supernova. The star before you has been building layers in its core like an onion: hydrogen fused to helium, helium to carbon, carbon to oxygen, oxygen to silicon, and finally silicon to iron, each stage releasing less energy and lasting a shorter time than the previous stage. Iron sits at the bottom of the energy curve. Fusion of iron consumes energy rather than releasing it, so when the core becomes pure iron, no more energy can be extracted through fusion. The iron core grows to about 1.4 solar masses, supported temporarily by electron degeneracy pressure. But fusion continues in shells around it, adding more iron to the core and pushing it toward instability. The iron core collapses when it can no longer support itself, gravity overwhelming the electron degeneracy pressure, and the collapse happens incredibly fast. In less than 1 second, the core shrinks from about 5,000 kilometers in diameter to about 20 kilometers. The protons and electrons in the core crush together to form neutrons, releasing enormous numbers of neutrinos that carry away most of the collapse's energy. And the neutrons briefly resist further compression through neutron degeneracy pressure. The infalling outer layers of the star, still moving inward at a significant fraction of light speed, slam into this suddenly rigid core and rebound outward. And the shock wave from this rebound travels outward through the star, heating and accelerating the layers above. Within hours, the shock wave reaches the surface. The star brightens dramatically, and the supernova becomes visible, reaching peak brightness within days and outshining entire galaxies for weeks. A supernova at peak brightness can shine with the luminosity of 5 billion suns, making it visible across millions of light years. And for a brief period, one dying star produces more light than all the hundreds of billions of normal stars in its host galaxy combined. The brightness arises from the enormous energy released, both from the collapse itself and from the radioactive decay of unstable isotopes created in the explosion. Particularly nickel-56, which decays to cobalt-56 and then to iron-56 over weeks to months. The light curve of a supernova, how its brightness changes over time, follows a characteristic pattern: rapid rise to peak brightness, then slower decline over months as the radioactive elements decay and the expanding debris cools. Type 2 supernovae, those from massive star core collapse, show hydrogen lines in their spectra because the star retained its hydrogen envelope, while type IB and IC supernovae come from stars that lost their hydrogen before exploding. The explosion scatters the star's contents into space at speeds of 10,000 to 30,000 kilometers per second, sending carbon, oxygen, silicon, iron, and heavier elements outward in an expanding shell of debris. The supernova creates elements heavier than iron through rapid neutron capture, the R process, where atomic nuclei absorb many neutrons in rapid succession before those neutrons decay, building up elements like gold, platinum, and uranium. These heavy elements cannot form through normal fusion. They require the intense neutron flux present during a supernova explosion or in neutron star mergers, making supernovae crucial to the production of about half the elements heavier than iron. The expanding debris carries these newly synthesized elements into the interstellar medium, enriching the gas from which future stars will form, seeding the galaxy with the raw materials for planets and life. Historical supernovae have been recorded throughout human history, bright new stars appearing where none existed before, visible even in daylight in some cases, then fading over weeks or months. The supernova of 1054 CE appeared in the constellation Taurus. Chinese and Arab astronomers recorded a star bright enough to see during the day for weeks. And today we see the remnant of that explosion as the Crab Nebula, still expanding outward from the explosion site, nearly 1,000 years later. The supernova of 1572, observed by Tycho Brahe, challenged the Aristotelian view that the heavens were unchanging, proving that new stars could appear and that the celestial sphere was not eternal and perfect. Kepler's supernova of 1604 was the last supernova visible to the naked eye in our galaxy. Another bright new star that appeared, brightened, and faded, leaving a remnant still visible today through telescopes. SN 1987A in the Large Magellanic Cloud became the closest observed supernova of the modern era, appearing on February 23, 1987, at a distance of about 168,000 light-years, close enough for detailed study with modern instruments. Astronomers detected neutrinos from the core collapse, the first and only time neutrinos from a supernova have been directly observed, confirming theoretical predictions about core collapse physics. The progenitor star had been identified in previous photographs, a blue supergiant called Sanduleic -69 degrees, 202, allowing astronomers to study what type of star exploded and compare observations with theoretical models. SN 1987 has been monitored continuously since the explosion, providing unprecedented data on how supernova remnants evolve, how the shockwave interacts with surrounding material, and how the expanding debris changes over decades. Betelgeuse, the red supergiant in Orion, could become a supernova at any time, or it might not explode for another 100,000 years, the uncertainty arising from our limited understanding of exactly when massive stars reach the iron core collapse stage. When Betelgeuse does explode, it will become as bright as the full moon as seen from Earth, despite being over 600 light-years away, visible during the day and casting shadows at night, dominating the sky for weeks before fading. The explosion will pose no danger to Earth at that distance. The radiation and particles spreading spherically and diminishing with the square of distance, but it will provide an unparalleled opportunity to study a nearby supernova with modern instruments. The event might have already occurred, the light from the explosion still traveling toward us, or it might happen tomorrow, or 1,000 years from now. We cannot know until the light arrives. Supernova remnants expand through space for thousands of years, creating beautiful structures as the shockwave interacts with the surrounding interstellar medium, sweeping up gas and compressing it, triggering new star formation in some cases. The Crab Nebula expands at about 1,500 kilometers per second, its filaments and wisps of gas showing where the shockwave has passed. And at the center, sits a pulsar, the neutron star remnant of the collapsed core. Cassiopeia A, the remnant of a supernova that occurred about 350 years ago, shows a similar structure with an expanding shell of debris moving at thousands of kilometers per second. And infrared observations reveal dust forming in the cooling ejector, grains of silicon, and carbon condensing from the gas. The Veil Nebula forms part of the Cygnus Loop, a supernova remnant from an explosion about 10,000 to 20,000 years ago, now spread across several degrees of sky and still expanding, though slowed by interaction with surrounding gas. The rate of supernovae in a galaxy depends on the galaxy's size and star formation rate. The Milky Way probably experiences 2 to 3 core collapse supernovae per century, on average, though many remain hidden by dust and distance, invisible from Earth, even though they occur in our galaxy. Andromeda, a larger galaxy than the Milky Way, might experience 3 to 4 supernovae per century, while small dwarf galaxies might see one every few thousand years. Astronomers detect supernovae in distant galaxies regularly, automated surveys discovering dozens per year in galaxies billions of light-years away, the explosions bright enough to be visible across cosmic distances. Type Ia supernovae serve as standard candles for cosmology, their consistent peak brightness allowing distance measurements to faraway galaxies, and observations of distant Type Ia supernovae led to the discovery that the universe's expansion is accelerating, driven by dark energy. The energy released in a supernova is staggering, about 10 to the power of 44 joules, equivalent to the energy the Sun will emit over its entire 10 billion year lifetime, released in just seconds. Most of this energy escapes as neutrinos, ghostly particles that barely interact with matter and stream freely out of the collapsing core, carrying information about the collapse at nearly the speed of light. Only about 1% of the energy goes into the kinetic energy of the explosion and the light we see. But even 1% of that total represents an enormous amount of energy. The supernova mechanism is complex, relying on neutrino interactions with the infalling material to drive the rebound shockwave outward, and computer simulations of core collapse still struggle to reproduce the explosion reliably, suggesting some physics remains incompletely understood. Supernovae enrich the universe with heavy elements, scatter the products of stellar nucleosynthesis across light-years of space, and trigger new star formation by compressing nearby clouds, making them vital to galactic chemical evolution and the cycle of stellar birth and death. Every atom of carbon, oxygen, iron, and silicon in your body came from a star that died, probably a supernova. The violent death scattering those atoms into space, where they eventually found their way into the molecular cloud from which the Sun and Earth formed. The iron in your blood was created in a massive star and released in a supernova explosion. The oxygen you breathe came from a different star that also died, possibly billions of years before the Sun formed. Supernovae connect us directly to stellar death, the dramatic, violent end of massive stars providing the elements necessary for planets and life. Beauty and destruction intertwined in the cosmic cycle. Type Ia supernovae differ from core collapse supernovae, arising from white dwarfs in binary systems rather than from massive star cores, and they reach slightly different peak brightnesses while following different light curves and showing different spectral features. A Type Ia supernova shows no hydrogen lines, because white dwarfs have lost all their hydrogen. And it shows strong silicon lines because the explosion involves fusion of carbon and oxygen to silicon and nickel. The consistency of type Ia supernovae, all resulting from white dwarfs reaching the Chandrasekhar limit, makes them valuable for cosmology, despite being less common than core collapse supernovae. The two types serve different roles. Core collapse supernovae enriching the galaxy with elements from helium to the heaviest elements. Type Ia supernovae providing primarily iron peak elements and serving as cosmic distance indicators. The supernova you witness completes in moments what took millions of years to build. Layers of carefully fused elements scattered to space. The star's entire life story erased in the explosion. Only the expanding remnant and the collapsed core remaining. The brightness floods across space, light that will travel for thousands of years before reaching distant galaxies, carrying information about the explosion encoded in the spectrum and light curve. The debris expands, cools, and gradually mixes with the interstellar medium, becoming indistinguishable from the background gas over hundreds of thousands of years, contributing to the slow enrichment of the galaxy with heavy elements. Somewhere in that expanding shell, atoms that will someday be part of planets' orbit, atoms that will be breathed by living creatures, atoms forged in this violent moment, now beginning their long journey toward new stars and new worlds. At the center of the supernova remnant, hidden within the expanding debris, lies the collapsed core of the massive star, an object so dense and strange that it challenges comprehension. A neutron star spinning rapidly as it formed, and now emitting beams of radiation like a cosmic lighthouse. The neutron star measures only about 20 kilometers in diameter, smaller than most cities, yet contains about 1.4 to 2 solar masses, the entire mass of a star compressed into a volume that would fit within Earth's atmosphere. A cubic centimeter of neutron star material weighs about 1 billion tons. Density so extreme that all of Earth's mass, compressed to this density, would fit in a cube about 300 meters on a side. Matter crushed beyond the point where atoms exist as separate entities. Protons and electrons in the collapsing core merged to form neutrons during the supernova. The intense pressure overcoming the electromagnetic repulsion between protons and the space electrons normally occupy, crushing them together and releasing neutrinos as byproducts of the transformation. The resulting neutron star consists primarily of neutrons packed tightly together, supported against further collapse by neutron degeneracy pressure, the same quantum mechanical principle that supports white dwarfs, but operating at much higher density. The neutrons themselves may break down in the very center of the most massive neutron stars, creating exotic matter called quark matter, where the fundamental constituents of neutrons exist freely rather than bound together. But current physics cannot definitively predict what exists at the very core under such extreme conditions. Surface gravity on a neutron star is about 200 billion times stronger than Earth's surface gravity, so intense that the surface is perfectly smooth. Any irregularity more than a few millimeters high would be crushed flat by the immense gravitational field. Space-time curves dramatically around a neutron star. Light from the back surface bends around to become visible from the front, allowing an observer above the pole to see more than half the surface at once. Anything dropped onto a neutron star surface would impact at about half the speed of light, releasing energy equivalent to thousands of nuclear weapons. And any object approaching too close would be torn apart by tidal forces long before reaching the surface. The escape velocity from a neutron star surface is about half the speed of light, making neutron stars the most extreme objects that can exist without becoming black holes. Pulsars are rapidly rotating neutron stars with strong magnetic fields, emitting beams of radiation from their magnetic poles that sweep across space as the star rotates. And if a beam happens to point toward Earth, we detect regular pulses of radio waves, X-rays, or gamma rays. The Crab pulsar at the center of the Crab Nebula rotates 30 times per second, spinning so fast that a point on its equator moves at about 1/10 the speed of light. And the rotation is slowly decreasing as the pulsar loses energy through magnetic radiation. The pulsar's period increases by about 38 nanoseconds per day, an incredibly small change that accumulates over time. Eventually, the pulsar will slow to the point where the emission mechanism shuts off, and it will cease to be detectable. Young pulsars rotate rapidly, hundreds or even thousands of times per second in some cases, while older pulsars slow down and eventually fade from detection as their rotation and magnetic fields weaken. PSR J1748-2446 AD holds the record as the fastest known pulsar, rotating 716 times per second, so fast that points on its equator move at about 1/4 the speed of light, despite the neutron star's small size. This millisecond pulsar must have been spun up by accreting matter from a binary companion, the infalling material carrying angular momentum that increased the neutron star's rotation rate, converting it from a slow, isolated pulsar to an extremely fast rotating one. Millisecond pulsars are remarkably stable, their rotation periods constant to better than 1 part in 10 to the 15th, making them potentially more stable than the best atomic clocks. And astronomers use arrays of millisecond pulsars as a galaxy-scale detector for gravitational waves. The extreme rotation rates push the neutron star toward the limit of how fast a stable object can spin. Any faster, and centrifugal forces would overcome gravity and tear the star apart. Pulsars slow down gradually as they radiate energy away, the rotation providing energy that drives the magnetic field and particle acceleration, creating the beams we detect. And conservation of energy means the rotation must slow as this energy escapes. The Crab pulsar powers the surrounding nebula through its rotational energy loss, the slowing spin rate providing energy that keeps the nebula glowing and drives the outflows visible in the nebula's structure. Young pulsars slow fastest, losing rotational energy at high rates, while old pulsars slow more gradually as their magnetic fields weaken and their rotation already reduced. Eventually, pulsars slow to periods of several seconds and become difficult to detect, the emission weak and the pulses infrequent, fading into the background of undetected neutron stars that populate the galaxy. Magnetars are neutron stars with the strongest magnetic fields known in the universe. Fields measuring 10 to the 14th or 10 to the 15th Gauss, 1 trillion times stronger than Earth's magnetic field, and 1,000 times stronger than typical pulsars. These intense magnetic fields, stronger than the magnetic field that can exist in normal matter without the quantum effects present in neutron stars, store enormous energy and cause the neutron star's crust to fracture occasionally, creating Starquakes. When the crust fractures, the magnetic field reconfigures suddenly, releasing energy in bursts of X-rays and gamma rays detectable across the galaxy. Brief flares lasting milliseconds to seconds that can outshine the entire galaxy in high-energy radiation. Magnetar flares detected from Earth have been intense enough to affect the ionosphere, despite originating thousands or tens of thousands of light years away, showcasing the extreme energies involved. The magnetic fields in magnetars decay over thousands to tens of thousands of years, making magnetars a transient phenomenon. Neutron stars that display magnetar behavior for a brief period before their fields weaken to normal pulsar levels. About 30 magnetars are currently known in the Milky Way, but thousands of inactive former magnetars likely exist. Neutron stars that were once magnetars, but whose fields have decayed below the threshold for observable activity. The origin of such strong magnetic fields remains somewhat uncertain, possibly arising from unusually rapid rotation in the newly formed neutron star, from dynamo effects during core collapse, or from the merger of two white dwarfs rather than single massive star core collapse. Different formation mechanisms potentially creating different types of neutron stars, binary pulsars, orbit companion stars, or other compact objects, providing laboratories for testing general relativity and studying orbital dynamics under extreme conditions. The famous Hulse-Taylor binary, consisting of two neutron stars orbiting each other every 7.75 hours. The orbit of the Hulse-Taylor binary decays measurably over time, the two neutron stars spiraling gradually closer as the system loses energy to gravitational waves, exactly as general relativity predicts, and observations spanning decades confirm the energy loss matches theoretical calculations to high precision. This binary will eventually merge in about 300 million years, the two neutron stars spiraling together and coalescing, possibly forming a black hole or a hypermassive neutron star, and emitting a burst of gravitational waves detectable across the universe. Neutron star mergers create some of the most energetic events in the universe after supernova explosions, the collision producing gravitational waves, gamma-ray bursts, and optical/infrared transients called kilonovae, powered by radioactive decay of heavy elements synthesized in the merger. The first detected neutron star merger, GW170817, occurred in August 2017, producing gravitational waves detected by LIGO and Virgo. A gamma-ray burst detected by Fermi and Integral, and an optical transient detected by dozens of telescopes, demonstrating multi-messenger astronomy. The merger site showed evidence for heavy element production, lanthanides and actinides, created through rapid neutron capture as the neutron-rich material from the merger decompressed, confirming that neutron star mergers produce about half of the elements heavier than iron, complementing the production in supernovae. The diversity of neutron stars, from slow isolated pulsars to millisecond pulsars to magnetars to binary systems, reflects the different evolutionary paths and initial conditions that created them, each type providing insights into extreme physics and stellar evolution. About 1 billion neutron stars likely populate the Milky Way, the remnants of massive stars that have died over the galaxy's history. Though only about 3,000 are currently detected as active pulsars, the vast majority being too dim or oriented wrong for their beams to cross Earth. Future surveys, particularly radio surveys, will discover more pulsars, and gravitational wave detectors will continue finding merging neutron star binaries, expanding our knowledge of these extreme objects and their role in cosmic evolution and element production. Standing near a neutron star, at a safe distance where tidal forces and radiation remain survivable, you would see space-time visibly warped, the strong gravity bending light around the star and allowing you to see more than half its surface at once. The surface would appear smooth and featureless, crushed flat by gravity, glowing with residual heat from its formation, or from particle impacts if the neutron star is still accreting material. If the neutron star is a pulsar, you might see jets of particles streaming from the magnetic poles, beams of radiation sweeping through space at the rotation period. And if you were in the beam path, the radiation would be lethal. High-energy photons and particles accelerated to near light speed. The neutron star represents matter in one of its most extreme possible forms, just shy of collapsing into a black hole, a cosmic laboratory where physics operates at limits we cannot reproduce on Earth. The James Webb Space Telescope drifts in orbit around the Sun-Earth L2 point, about 1.5 million kilometers from Earth. Its massive gold-plated mirror and infrared instruments opening new windows on stellar phenomena that previous telescopes could barely glimpse. Launched on December 25th, 2021, and beginning science operations in July 2022. JWST operates primarily in infrared wavelengths from about 0.6 to 28 micrometers, allowing it to see through dust that blocks visible light and to observe very distant objects redshifted into infrared by cosmic expansion. The telescope's capabilities particularly suit it for studying star formation, observing cool stars and brown dwarfs, examining supernova remnants, and searching for the earliest stars in the universe, complementing visible light telescopes like Hubble, while revealing phenomena invisible at shorter wavelengths. JWST has imaged star-forming regions in unprecedented detail, peering through the dusty cocoons that hide protostars from visible light telescopes and revealing the full population of forming stars. The Carina Nebula images released in July 2022 as part of JWST's first public images show hundreds of previously unseen protostars embedded in the cosmic cliffs, a region where intense ultraviolet radiation from massive stars erodes a molecular cloud. The infrared view reveals forming stars as bright points within the dark, dusty columns, objects completely invisible to Hubble in visible light, but clearly detected by JWST's infrared instruments, showing where new suns are being born right now. The images also showed jets from young stars, Herbig-Haro objects glowing where these jets impact surrounding gas, and the complex structure of the nebula, shaped by stellar winds and radiation. The pillars of creation, first made famous by Hubble's 1995 visible light image, appear even more spectacular in JWST's infrared observations, released in October 2022. The infrared view penetrates the dust that appears opaque in visible light, revealing forming stars inside the pillars themselves, red and orange points marking protostars embedded deep within the columns. The detailed structure shows how the pillars are being eroded by radiation from nearby massive stars, the tips evaporating and revealing the stars within, the same process that will eventually destroy the pillars entirely over the next few million years. JWST's near-infrared and mid-infrared images complement each other, the near-infrared showing more stars, while the mid-infrared highlights the dust structure, together providing a complete view of the star-forming region. JWST can detect and characterize brown dwarfs and free-floating planets, objects too cool and dim for most previous telescopes to study effectively. Measuring their temperatures, compositions, and atmospheric properties through infrared spectroscopy, brown dwarfs, with temperatures below about 400 degrees Celsius, emit most of their light in mid-infrared wavelengths, making them ideal targets for JWST, despite being essentially invisible to optical telescopes. Early observations have discovered extremely low-mass brown dwarfs near the deuterium burning limit and free-floating planetary mass objects in young star clusters. Objects that formed like stars but never achieved sustained fusion. These discoveries help define the boundary between planets and stars, understanding the minimum mass for fusion and the properties of objects that fall below that threshold. The search for population 3 stars, the very first generation of stars formed from primordial gas containing only hydrogen and helium, without any heavy elements, represents one of JWST's major scientific goals. These first stars, predicted to be very massive and very hot, lived and died early in cosmic history, and while we have never directly observed one, their existence is inferred from the heavy elements present in later generations of stars. JWST's ability to observe very distant galaxies, seeing them as they appeared billions of years ago, when the universe was young, provides the best opportunity yet to detect population 3 stars, or their immediate descendants. The telescope has detected galaxies from when the universe was only a few 100 million years old, pushing observations closer to the era when the first stars should have formed. Observing extremely distant galaxies means looking back in time, the light from these galaxies traveling for billions of years before reaching us, showing the galaxies as they were in the distant past, rather than as they are now. Galaxies at redshift 6 or 7 appear as they were about 12 to 13 billion years ago, when the universe was less than 1 billion years old, and JWST has detected galaxies at even higher redshifts. These early galaxies contain stars formed from gas with very low metallicity, close to the primordial composition, and studying their spectra reveals what the first and second generations of stars were like. The heavy elements we detect in these early galaxies, carbon, oxygen, silicon, came from early supernovae, showing that massive stars were already forming, living, and dying within the first billion years of cosmic time. JWST's infrared spectroscopy capabilities allow it to measure the chemical composition of stellar atmospheres, determining which elements are present and in what abundances, providing information about stellar evolution and galactic chemical enrichment. Observations of cool red giants show carbon and nitrogen abundances that reveal what fusion processes operated during the star's life, while observations of hot blue stars show surface abundances of helium and nitrogen that indicate mass loss and mixing processes. Metal-poor stars from the galactic halo show compositions reflecting the early universe's element budget, while metal-rich stars from the disk show enrichment from many generations of stellar nucleosynthesis. The spectra tell the chemical history of the galaxy, written in the abundances of elements synthesized in successive generations of stars. Supernova remnants observed in infrared reveal warm dust forming in the cooling ejecta, grains of silicon, carbon, and iron condensing from the gas, as the expanding debris cools below a few thousand degrees. Cassiopeia A, the remnant of a supernova about 350 years ago, shows complex dust structures in JWST observations, freshly formed dust grains absorbing and re-emitting light in infrared wavelengths. The dust formation is important because supernovae may be a major source of cosmic dust, grains that will eventually become incorporated into molecular clouds and help cool collapsing regions during star formation. JWST's observations help quantify how much dust forms in supernova remnants and what types of grains form, constraining models of dust production and evolution in galaxies. Wolf-Rayet stars, massive, evolved stars that have lost most of their hydrogen through powerful stellar winds, show prominent emission lines in their spectra and shed mass at high rates, creating spectacular nebulae around themselves. These stars represent late stages of massive star evolution, objects that will explode as supernovae within a few 100,000 years. And their strong winds and intense radiation shape the surrounding environment. JWST observations of Wolf-Rayet stars show detailed structures in their circumstellar nebulae, shells and bubbles of previously ejected material glowing in the starlight. And the spectra reveal abundances, showing the products of CNO cycle and helium fusion exposed at the surface. WR140 provides a spectacular example. The star surrounded by concentric shells of ejected material, creating a cosmic rose visible in infrared light. Eta Carinae, one of the most massive and luminous star systems known, periodically erupts with enormous mass ejections, and JWST observations reveal the complex nebula surrounding this system in unprecedented detail. The Great Eruption of the 1840s ejected more than 10 solar masses of material at high speed, creating the Homunculus Nebula, a bipolar structure of dust and gas expanding from the star. JWST's infrared view shows dust in the nebula, molecular hydrogen, and the structure of multiple eruption events, helping astronomers understand what causes such massive eruptions in very luminous stars. Eta Carinae will likely explode as a supernova or hypernova in the astronomically near future, perhaps within the next million years. And studying it now provides insights into the final stages of very massive star evolution. JWST has detected organic molecules in the vicinity of young stars, seeing complex carbon-based molecules in the planet-forming disks around protostars, suggesting that the chemical building blocks of life form naturally during star and planet formation. Observations of protoplanetary disks show water ice, carbon monoxide, carbon dioxide, methane, and more complex organic compounds, the inventory of molecules that will be incorporated into planets and comets. These observations connect star formation to planet formation and potentially to life, showing that the same processes that create stars also create the chemistry necessary for biology, at least the carbon-based life we know. The presence of complex organic molecules in star-forming regions suggests that the ingredients for life arise naturally and commonly wherever stars and planets form. Each JWST discovery adds to our understanding of stars. From their formation in dusty nebulae, to their evolution through various stages, to their deaths in planetary nebulae or supernovae, and the remnants they leave behind. The telescope's infrared eyes see what visible light instruments cannot, revealing the hidden universe of cool objects, dust-shrouded regions, and extremely distant early stars. The observations complement studies from other telescopes operating at different wavelengths. Radio observations revealing cold molecular gas, X-ray observations showing hot plasmas and compact objects, optical observations providing detailed spectra and images, all together building a complete picture of stellar phenomena. JWST's mission is planned for at least 10 years with enough fuel for possibly 20, promising many more discoveries about stars and their life cycles in the coming decades. The images from JWST carry an aesthetic quality beyond their scientific value. Beautiful structures and colors that inspire wonder, even in viewers who do not understand the detailed astrophysics, serving as reminders that the universe contains beauty as well as information. The golden mirror, infrared instruments, and patient observations bring back visions of nebulae and galaxies and forming stars that connect people to the cosmos, showing that the universe is not cold and empty, but filled with structure and process and ongoing change. Stars are born, live, and die in beautiful ways, their light carrying information across space and time. And telescopes like JWST allow us to witness phenomena that would otherwise remain forever hidden, expanding human knowledge and feeding the quiet wonder that drives scientific exploration. The atoms in your body, the oxygen in your lungs, the carbon in every cell, the calcium in your bones, the iron in your blood, all originated in stars. And this simple fact connects you directly to the stellar life cycles we have explored together tonight. The Big Bang created hydrogen, helium, and traces of lithium, the three lightest elements. Formed in the first few minutes after the universe began, when temperatures and densities were high enough for nuclear fusion. Everything else, every element heavier than lithium, formed later inside stars through fusion or in supernovae through explosive nucleosynthesis, gradually enriching the universe with heavy elements as stars lived and died. Carbon formed through helium fusion in red giants, oxygen through oxygen fusion in massive stars, iron through silicon fusion in the final moments before core collapse. Each element arising at specific temperatures and pressures in specific stellar environments. When stars die, they return their accumulated elements to space. Planetary nebulae gently releasing carbon, nitrogen, and oxygen from sun-like stars. Supernovae violently expelling elements from carbon to uranium from massive stars. The ejected material mixes with the interstellar medium, spreading through molecular clouds, becoming incorporated into new generations of stars and their planetary systems. Our solar system formed about 4.6 billion years ago from a molecular cloud that contained hydrogen and helium from the Big Bang plus heavy elements from previous stellar generations. Multiple earlier stars contributing atoms to the material that became the Sun, Earth, and everything on it. The Sun is a third-generation star, possibly fourth or fifth generation, made from material that cycled through previous stars, each cycle adding more heavy elements and increasing the metallicity. Every breath you take contains oxygen atoms that were created in a massive star billions of years ago, fused from lighter elements in the star's core, then scattered into space when that star exploded as a supernova. The carbon in your DNA, formed through the triple alpha process in a red giant's core. 3 helium nuclei combining to form 1 carbon nucleus, a reaction that occurs at specific temperatures around 100 million degrees. The calcium in your bones came from oxygen fusion in massive stars. Multiple fusion reactions building heavier nuclei from lighter ones. And the iron in your hemoglobin formed through silicon fusion or was created in the supernova explosion itself. Each element has its own origin story, its own stellar source, and together they form you, a collection of stellar material, temporarily organized into a living, breathing, thinking arrangement. The atoms in your left hand might come from different stars than the atoms in your right hand. The solar nebula mixing material from multiple sources. Previous supernovae and planetary nebulae, all contributing to the cloud from which the sun formed. Some atoms in your body are older than Earth, remaining unchanged since they formed in stars billions of years ago, while others have cycled through living organisms countless times, becoming part of bacteria, plants, animals, and humans before arriving in your body now. The carbon cycle on Earth continuously recycles carbon atoms through the biosphere. But those carbon atoms originally came from stars, created through fusion, scattered through space, incorporated into the forming Earth, and now cycling through life on the planet's surface. Gold, silver, platinum, and uranium in Earth's crust formed through rapid neutron capture, the R process, which occurs in supernovae or in neutron star mergers, where neutron-rich material undergoes a cascade of neutron captures faster than radioactive decay can occur. These heavy elements cannot form through normal fusion, requiring environments with enormous neutron fluxes available only in the most extreme stellar events. The gold in jewelry, electronics, and geology was created in neutron star mergers or supernovae, violent events that scattered heavy elements across space, where they eventually accreted into planetary bodies. Every element heavier than iron arose through these processes, making supernovae and neutron star mergers crucial to the existence of the heavy element inventory we see in the universe. The metallicity of stars increases over cosmic time. Early stars formed from nearly pure hydrogen and helium, while stars forming today incorporate carbon, oxygen, iron, and other heavy elements from previous stellar generations. Our Sun's metallicity is about 1.5% by mass, meaning 1.5% of its mass consists of elements heavier than helium, the rest being hydrogen and helium. This metallicity reflects billions of years of stellar evolution and element production, the gradual enrichment of the galaxy through successive generations of stars. The first stars, population 3, had essentially zero metallicity, containing only primordial hydrogen and helium, while the most recent stars, population I like our Sun, show significant heavy element abundances from all the stars that lived and died beforehand. Looking at stars means looking at the factories that created the elements. Fusion reactors operating for millions to billions of years, slowly converting hydrogen to helium and helium to carbon and carbon to heavier elements through the patient operation of nuclear physics. A red dwarf fusing hydrogen will operate for trillions of years, creating helium that might never fuse further if the star lacks sufficient mass. A massive blue star will race through its fuel in millions of years, creating carbon, oxygen, silicon, and iron before exploding and scattering those elements. The Sun sits between these extremes, fusing hydrogen for 10 billion years, eventually fusing helium to carbon and oxygen in its red giant phase, then ending as a white dwarf, while a planetary nebula returns its nucleosynthesis products to space. The cycle continues. Enriched gas forms new molecular clouds. New stars form from enriched material. Those stars create more heavy elements, die, and enrich the gas further. A cycle operating for the 13.8 billion year history of the universe and continuing into the indefinite future. Each cycle increases metallicity slightly, making planets more likely to form because heavy elements provide the rocky and icy material planets need. Hydrogen and helium alone cannot create solid planetary bodies. Earth-like planets require carbon, oxygen, silicon, iron, and other heavy elements, all products of stellar nucleosynthesis, making stars essential not just for energy, but for the material existence of planets and life. Without previous generations of stars, Earth could not exist, lacking the heavy elements that form its core, mantle, crust, atmosphere, and oceans. "We are made of star stuff," as Carl Sagan famously said, a poetic statement that is also literally scientifically accurate. Every atom in your body, except hydrogen, formed inside a star. The awareness of this connection changes how we look at stars. They are not just distant lights, but our ancestors in a meaningful physical sense, the sources of the material from which we are made. Looking up at the night sky means looking at the furnaces that created you, fusion-powered suns that operated billions of years ago, synthesizing elements, dying, scattering those elements to space, allowing new stars and planets, and eventually, life to form. The light from those stars carries across space, some stars still shining, others long dead, but all connected to us through the elements they created. The Sun itself will return elements to space in about 5 to 7 billion years, becoming a red giant, shedding its outer layers as a planetary nebula, scattering carbon and nitrogen into the interstellar medium. The material from the Sun and Earth, torn apart and dispersed during the red giant phase, will eventually mix with the galactic gas, possibly forming new stars billions of years hence. The atoms that currently form Earth, that form your body, that form the air and water, will be scattered and recycled, some perhaps becoming part of new planets in new solar systems in the distant future. The cycle operates on timescales far beyond human lifetimes or civilizations. But it continues, the endless churning of matter through stars and space, and back to stars again. Understanding our stellar origins provides a cosmic perspective, situating human existence within the larger context of the universe's history and evolution, showing that we are not separate from the cosmos but integral parts of it. The same physics that operates in stars operates in our bodies. The electromagnetic forces that bind atoms, the weak nuclear force that allows radioactive decay, all the fundamental forces participating in both stellar evolution and biological processes. The energy that powers life on Earth comes from the Sun's fusion reactions, photosynthesis capturing photons created by fusion 8 light minutes away, storing that energy in chemical bonds, passing it through ecosystems. Life as we know it depends on stars for both the elements it's made of and the energy it runs on, a double connection that makes stars essential to biology. The 100 facts we have explored tonight, from star sizes to colors to formation to death, to exotic remnants, to discoveries, to connections, all tell the story of stars and their role in the universe and in our existence. Stars dominate the visible universe, the lights we see when we look up, the sources of heavy elements, the drivers of galactic evolution, the potential homes for other planets and other life. Understanding stars means understanding the universe's visible matter, how it organizes, evolves, creates complexity, and cycles through different forms over cosmic time. The more we learn about stars, the more we understand about where we came from and where we fit in the larger cosmos. Knowledge that connects us to the universe and satisfies the deep human curiosity about origins and meaning. The peaceful wonder of knowing these facts needs no drama, no exaggeration, no artificial awe. The reality is remarkable enough on its own. You are made of atoms from stars. Those stars lived for millions to billions of years creating those atoms scattered through space and eventually became part of you. And someday they will return to space and the cycle will continue. This fact is both humbling and uplifting, showing that we are small in cosmic terms, but also integral to cosmic processes, temporary arrangements of stellar material that somehow achieved consciousness and can contemplate their own origins. Stars made us. We study stars. We understand our connection to stars. And in doing so, we complete a circle of awareness that spans billions of years and light years of space. Tonight, we have drifted among stars from the smallest to the largest, from the hottest to the coolest, from birth to death, from the familiar to the exotic, from the distant past to the present to the far future. We have seen red dwarfs and blue giants, planetary nebulae and supernova remnants, pulsars and white dwarfs, star-forming regions and JWST discoveries. We have learned that stars come in tremendous variety, but all follow paths determined by their masses, that they create the elements necessary for planets and life, that they die in different ways, but all return material to space, that new generations form from enriched material in an endless cycle. The knowledge sits quietly, facts about the universe, information about how things work, and underneath it all, the gentle recognition that we belong to this process. We are part of the cycle. We are stellar material that has organized itself to understand stellar material. Rest now among the knowledge of stars, the 100 facts settling into memory, images of nebulae and giants and tiny dwarfs, drifting through thought as sleep approaches. The stars continue shining whether we watch them or not. Fusion proceeding in countless cores across the galaxy, light traveling through space, new stars being born while old stars die, the cycle continuing through the night, and through tomorrow, and through billions of years to come. We are connected to all of it, made from it, temporarily aware of it, grateful for the light and the elements, and the beauty that stars provide. The lights that made you shine tonight, as they have for billions of years, patient stellar furnaces creating, living, dying, enriching, cycling, continuing, eternal in the aggregate, if not individually. And you are part of that story, temporary but real, small but meaningful, stardust contemplating stars, atoms understanding atoms, the universe aware of itself, peacefully complete.